All right. On that cheerful note, we have a short announcement, and then we'll get the show on the road. You don't really need that because it's local, but
Hi, I'm Peter Milford. I'm CTO at iFluence Inc. And I just wanted to let everyone know we had a recent press announcement announcing our funding. We just closed a round of about $14 million. We're developing wearable eye tracking technology for upcoming wearable display devices like a VR headset or an augmented reality headset. So we do have several jobs listed on our website, so I encourage you to have a look and recommend it to all your friends. Hopefully I'll be able to give a talk in not too distant future and show some of our technology, but we're still mostly in stealth mode. I also have a handful of old fourth dimensions that I brought with me that anyone's welcome to, so please help yourself. I'm just sitting back there. All right, thank you.
Does that mean it's my turn? Okay. Only if it's my turn. Okay. Okay, does that work? You don't know, do you? Anyway, I'm Charlie Shattuck. I'm with Green Array Incorporated. And there have some good news and bad news this year. The good news is that Green Arrays is kind of hard at work. Some of the engineers there, including Greg Bailey, on a project that I can't talk about, sorry, but maybe someday soon. But the bad news is Greg won't have anything to say, so you're stuck with me. Sorry. I've got 3 speakers lined up, basically. We have Daniel Kalny is going to be speaking via video from the Czech Republic, and he'll go first. We have Mengpo and Mike, I don't know their last names, I'm sorry, from UC Berkeley are going to talk about... Pardon? The Bears, yeah, right. Yeah, they're from Cal. They're going to talk about some work they've done with the GA144. And at the end of that, I'm going to talk about this C virtual machine that Stefan Mauerhofer, with a tiny bit of help from me, has been working on. So, Dennis, can I get Daniel's video started now? All right. And while he's on, should I turn this off so that you don't hear me breathe and stuff? Or just put it further? Yeah, in theory. Let's say in theory I do. Okay.
you do not want to turn that off because then you turn your mic off because
gotcha.
That is how the internet hears him.
Okay, through my mic?
Your mic.
Oh, okay. I'll just be careful what I say.
Yes.
Let me see. Why is it not? Oh, right. Okay. I thought I was on a different program. Sorry, folks. Just a second. Full screen is what I want. Okay, I think we're ready to go.
Hi, my name is Daniel Kalny, and in the following presentation, I'm going to talk about the near-field magnetic induction communication system implemented with the Green Array chip GA144.
Okay, time out then. Sorry, Daniel.
Is a wireless form of a short-range communication using modulation of magnetic flux for data transmission.
Find it, yeah.
Magnetic field energy is transmitted and received through resonant coupling of inductors. Compared to other short-range communication technologies such as
this is wonderful, isn't it?
SVFIG has much lower power requirements, operates at shorter ranges from centimeters up to...
There's a pause. Okay, I understand now. Okay, sorry, Daniel. We're going to restart here, trying to get it figured out. I'm plugged into the microphone port. Is that correct?
Computer
is my
using the microphone. Oh, the headphone jack on the wrong one. That's why.
Oh,
there you go.
Okay, now see if I can get my volume. Yeah, exit is F11. Okay.
Now start the video over again.
I will. Okay, I've got full volume. Okay. Now, let's see if I can start the video. Okay, we're restarting. Let's see if this works.
My name is Daniel Kalny, and in the following presentation, I'm going to talk about a near-field magnetic induction communication system implemented in the Green Arrays chip GA144. Near-field magnetic induction communication is a wireless form of a short-range communication using modulation of magnetic flux for data transmission. The magnetic field energy is transmitted and received through resonant coupling of inductors. Short-range communication technologies such as Bluetooth and FMI has much lower power requirements, operates meters up to a couple of meters, and at slower data speeds. A major advantage of NFMI communication over traditional electromagnetic RF-based systems is that the magnetic induction waves are not generally affected by the environment, allowing communication through obstacles such as water and human body. Therefore, NFMIC targets the medium-capacity personal area networks with close proximity. There are NFMI technologies using higher carrier frequencies, such as NFC operating at 56 MHz. Alternatively, long wavelength signals with carrier frequencies below 450 kHz can be used, as is described in an IEEE 1902.1 standard. The physical layer of the NFMIC system shown in this presentation is based on the standard. It uses carrier frequency of 131 kHz, 1024 bits per second data rate, amplitude shift key modulation, and biphase mark encoding. Frame format is a simplified form of that described by the standard. Each frame starts with 12 synchronization bits, followed by an arbitrary number of 16-bit data words. The frame ends CRC using CCIPT 8-bit polynomial and a trailing sequence of 8 0 bits. The content of data words does not correspond to the standard definition and is defined by a higher level protocol. The system presented here is implemented using a green arrays evaluation board and a simple communication module. The module has a separate transmitter and receiver circuits. The transmitter uses an op-amp with a positive feedback to amplify voltage generated by an analog node across a load resistor to ground. The voltage gain of the op-amp is about 10. The output of the op-amp is fed into a series LC tank circuit with resonant frequency of 131 kHz. The receiver circuit is very similar to the transmitter. Oscillations of magnetic field create an induced voltage in the parallel resonant LC circuit. The induced voltage is amplified with an op-amp and fed into an analog node. The voltage gain of the positive feedback is about 100. Based on experiments with the circuits, I have later added a parallel 3K3 resistor to the receiving LC tank circuit in order to decrease the quality factor and suppress signal overshoot. The communication module uses the same antennas for transmission and reception. The antennas are made of about 190 turns of enameled copper 31 gauge wire bound in 2 layers around a ferrite rod core. The inductance of each antenna is about 330 microhenry. The op-amp used is a dual CMOS op-amp DLV342 manufactured by Texas Instruments. The 2 antennas are located on the other side of the PCB. Although the circuit is not an ideal for signal transmission and reception, the advantage is its simplicity low component count, and the same supply voltage as that for GA144, 1.8 volts. And no level shifters are needed between GA144 and the module. Greenery chips are by no means ordinary microcontrollers, and it is therefore not surprising that the procedure of their programming also requires unusual methods. The first step in programming a GA chip is to carry out a thorough floor planning. We start with the definition of input-output requirements. An application may need several GPIO or analog pins, or any available parallel or serial buses. In any case, we need to locate the nodes with input-output capabilities and perhaps try several combinations to find the optimal locations. As the code in GA chips is often data-driven, the next step is to define logical data paths within the application. The path is defined in such a way as to allow data to enter at the beginning, to be processed along the path, and to exit at the end. Data entering a path are to be processed according to a given algorithm. Such an algorithm has to be decomposed into small pieces of sequential code that can be individually implemented in nodes. For a more complicated code, one can divide the execution between several nodes. In such a case, one node is controlling the code execution, while the others are cooperating and execute their code on demand. GA chips also provide for a very efficient method of code execution, so-called code execution. In this case, a node executes code that is fed into its port by another node. This is a very powerful technique and is often used. The floor plan for the NFMIC system presented here requires one GPIO pin to connect a quartz crystal used to generate the carrier frequency. We also need one analog output for transmitter part of the communication module and one analog input for receiver. Although analog nodes of GA144 include both input and output pins, it is more efficient to split both paths and use two separate analog nodes. The whole system can be divided into three blocks: a clock generator implemented in the node 715, a transmitter path starting at the node 615 and ending at the analog node 717, and a receiver path starting at the analog node 713 and ending at the node 612. The NFMIC system, as shown here, is able to function independently of other codes running in the chip. It is sufficient to feed data to be transmitted into the node 615 and to read any data arriving via receiver path from the node 612. The data can be provided by neighboring nodes running an application via IDE path through an async serial link during the development, or by a polyfourth virtual machine running at the same chip and using ganglion messages to deliver data to and from the NFMIC system. Whatever the method, the system is absolutely oblivious to its nature. Before discussing any code, I will briefly describe a function of individual nodes. The first one is the node 715 functioning as a clock generator. The algorithm for driving a quartz crystal connected as shown here has been described in a GA application node. Here the code has been modified so that the oscillator can be activated and stopped at any time. The oscillator is running only when an NFMI transaction is required and halted otherwise to save the energy. The transmitter path starts at the node 615, implementing a serializer. This node converts an incoming data stream of 16-bit words into a stream of bits, the most significant bit first, and feeds the serial bit stream into the node 616. The node 616 implements a framer, which constructs a frame by prepending synchronization bits in front of the data bit stream, calculates CRC, and appends the checksum at the end of the data stream. Finally, it appends a closing 0-bit sequence. The whole frame is fed on the fly into the node 716, which encodes the incoming bits into marks and spaces according to biphase coding. Finally, the node 717 reads marks and spaces from the node 716 and modulates an output signal with corresponding waveforms by setting its analog output to a predefined voltage on the ground. The changes in the output pin are gated by the shared pin 17 that is internally connected to the pin 17 of the coarse oscillator. The transmission runs until the node 615 is informed about the end data. Then the frame is closed, and soon the transmission is finished. When the modulator suspends, the whole path is ready for another transmission. The receiver path starts at the analog node 713. The code here emulates a detector of a simple radio receiver. It implements several routines used to calibrate the ADC, to determine instantaneous voltage at the analog input pin, and to measure the maximum amplitude of the incoming signal. It can also provide an information whether there is any signal present at the analog input pin. All these functions are executed when requested by the neighboring node 714. All those requests originate from the node 614. When receiving a signal, the node 714 samples it at a frequency of 8 times the carrier frequency. It then applies a filter to generate an amplitude envelope of the incoming signal. The filtered signal is fed into the node 614, which recognizes rising and falling edges of the envelope and decodes the incoming signal into a stream of bits. Of the three nodes, the node 614 is the one that controls the whole cluster. Other two nodes just execute their code upon a request from the node 614. The stream of bits is then forwarded into the node 613, where data are separated from the rest of the frame and the CRC is calculated. The data bit stream is finally sent to the node 612, which implements a deserializer, reconstructing 16-bit data words and making them ready for reading. Since a frame may have an arbitrary length, the system has to know when to stop transmitting or receiving a frame. In order to signal the end of transmitted data, I have exploited a simple fact that GA chips use 18-bit wide words, while only 16 lower bits are used for transmitted data. Therefore, when a word with the bit 17 set high is read by the node 615, it is recognized as the end of data stream and the process of closing the frame starts. On the receiver side, there is no such possibility to indicate the end of frame. Both CRC and the last 80 bits of the frame cannot be distinguished from regular data. Hence, the decoder in the node 614 has a timeout loop which signals the end of frame if there is no amplitude change longer than what corresponds to 2 bits. When it happens, the node 614 stops ADC in the node 713 to save the energy and informs the node 613 of the end of frame. The node 613 then finishes the calculation of CRC and passes the result of the check down the stream with the bit 17 set high to signal the end of frame. This signal is then forwarded by the node 612 as the last data word to any recipient. It's up to the higher level protocol to check the CRC result and to take any further action. One more remark to the receiver data path. The node 612 does not provide any buffering capacity. If at the time of data word availability there is no neighboring node reading the data word is simply discarded in order not to suspend the node 612 and consequently the whole data path. It is the responsibility of the higher level protocol to wait for data from the node 612. It could be interesting now to have a look at a signal generated by the transmitter and how it looks like when received by the communication module and processed by the receiver path. In order to find out what happens with the signal outside the GA144 chip, an oscilloscope is a tool of choice. As you will see shortly, the GA chip itself can be used as a probe for the same purpose when the signal inside the chip is to be tested. In fact, with GA chips, this is a very simple task. Before discussing the measurement results, I'll briefly elaborate on the idea of using a GA chip as a probe to test itself. Due to its modular nature, the code used for the NFMIC system can be easily modified for experimentation with the signal transmission and reception. For a signal generation test, I only needed the oscillator, encoder, and modulator nodes. Instead of reading a stream of bits, the encoder is supplied a required mark and space sequence as a ganglion message. It can be anything from a simple carrier signal to any complicated sequence of marks and spaces. The point is that the exact moment when the sequence starts can be controlled from the polyforth code. A ganglion message can also be used to set a transmitter power. This is the voltage that DAC uses for signal generation. The oscillator itself can be controlled via ganglion messages. The receiver is also simplified so that only detector, sampler, and decoder nodes are used. As in the case of the transmitter, we don't need to receive a stream of bits. Rather, we are interested in raw or processed data from the ADC. Therefore, using ganglion messages, we download a stream of numbers from the ADC into a memory controlled by polyforth and then treat the recorded data offline. The advantage of using a chip itself as a test tool is that both transmission and reception of the signal can be initiated in a concerted fashion, and the test software can be written in high-level polyforth, which also runs on the same chip. Thus, the chip contains everything we need to test our design. It should be kept in mind, however, that the transfer function of ADC in GA144 is not linear in the whole range of allowed input voltages. As you can see on this record determined experimentally, the transfer function has a sigmoid shape. For that reason, the signal is distorted and the resolution degraded near the extremes of the acceptable voltage span. Although the ADC does not provide accurate values, it is still useful for visualization of an overall shape of a signal. So the voltages determined by ADC presented in the following records are approximations only. Let's start with the transmitter. For the sake of clarity, the following oscilloscope traces have been generated with a burst of carrier signal lasting for 8 periods only. First, I wanted to check that the output of the analog node 717 is a good square wave signal with correct frequency and amplitude. A snapshot of a scope screen confirms the generator works correctly. I was also interested to see how the signal is modified by the LC resonance circuit. A signal measured with an oscilloscope between inductor and capacitor is shown in the second picture. It is worth to note the slowly rising and falling edges of the transmitted signal envelope. Also, a ringing of the LC tank circuit is visible as the signal is longer than the driving square wave burst. The oscillations visible at the start of the trace come from a pulse sent to trigger the oscilloscope and are not related to the signal itself. On the receiver side of the module, I have recorded a scope trace at the output of the op-amp. The recorded signal is rectified due to a non-symmetrical power supply of the op-amp. The ringing of the signal is even more enhanced here. Again, the signal at the beginning of the trace comes from the triggering pulse. Interestingly, the trace recorded with an oscilloscope can be compared with the same signal recorded by the GA chip itself. As you can see, the overall shape of the recorded traces is very similar. This confirms that the chip itself can be used to record the received signal. In the following part, I am using a full-length signal of 128 oscillations of the carrier, as only an envelope of the signal is significant. The raw signal as received by the module and digitized by decoder node is shown in the first recorded trace. A detailed profile of the same signal is depicted in the second picture. Each point represents a single value determined by ADC. As noted earlier, the sampling rate is 8 times the carrier frequency. At the beginning of signal reception, the detector node determines an amplitude by taking 8 samples and looking for the maximum voltage. The value is used later for signal decoding, as I will explain shortly. The received signal is then passed through a digital filter. The filter is based on a simple algorithm. First, the difference between the last filtered value and the current raw signal value is calculated. Then, when the signal is rising, the difference is added to the last filtered value to get a new one. Thus, the signal is passed through the filter without any modification. On the other hand, when the signal is going down, a factor of 1/16 is used to slow down the decline. This way, an amplitude envelope shown here is obtained. The residual oscillations do not cause any complication in further signal processing, as will be shown in a short time. The detail of the signal after filtration is shown here. The advantage of this algorithm is that only fast write-shift instructions are used to get the reduced signal value. The next task of the decoder is to determine the length of signal between two consecutive edges. Thus, I have implemented a software analog of a Schmitt trigger and a pulse width measurement. The amplitude value determined earlier is converted into an upper and lower hysteresis limits. The calculation is again simple and fast, as the limits are set as 1/4 and 3/4 of the maximum. Then the code in the detector compares the current filtered signal value with these two limits and records the moment when the value exceeds the upper limit during rise of the signal, or the current value goes below the lower limit when the signal is falling. This way, the signal envelope is converted into a square wave. It is a simple matter of counting the number of samples between the square wave edges to determine whether a 0 bit or a 1 bit is being received. According to the biphase mark coding, the 0 is coded as a mark or space of a duration of 1 clock cycle, while a 1 bit is coded in such a way as to have a level change in the middle of the bit. This coding was the original frequency modulation in single density floppy disks. The advantage of the coding is that when marks and spaces are exchanged, the code is still valid. This is important in NFMIC, as rotating the ferrite antenna by 180 degrees changes the direction of the magnetic flux and consequently the polarity of the signal received. To determine out of the BMC signal whether a 0 or 1 bit is being read, the decoder counts the number of samples between two edges. As the data clock period is 128 carrier cycles per bit at the sampling rate of 8 times the carrier frequency, the bit length corresponds to 1024 samples. If the count is greater or equal to 3/4 of this number, this is 768 samples, the bit is considered 0. On the other hand, if the count is lower than that number, the level of the signal is taken into account. When the signal went high, then the count is ignored and the second interval is counted. When the signal went low, the bit is considered as 1 and the next interval is ignored. The counter restarts each time an edge is detected. The 3/4 limit for distinguishing between 0 and 1 bits is sufficient to provide for a high robustness with respect to differences in carrier frequency and the sampling rate. This is necessary as the asynchronous nature of GA chips prevents an exact time measurement using 4 next loops. The same experimental setup has also been used to determine how far the signal can reach and what is the effect of transmitter DAC amplitude on the reach of signal. The first graph shows the dependence of signal intensity, measured as the maximum amplitude of the received signal, on the distance between antennas. The experiments were carried out at different transmitter DAC output amplitudes. The measured data confirm the fact that the signal in the near field has a sharp roll of decaying as an inverse sixth power of distance. This is why the NFMIC is well suited for prior data transmission in a so-called secured communication bubble. Moreover, it promotes frequency reuse over short distances and also contributes less interference with other existing radio frequency communication systems. The next graph then shows the reach of the signal defined as the distance of a 6 decibel signal attenuation versus the transmitter DAC amplitude used. Increasing the DAC amplitude increases the reach of signal. However, it shows that the design of the module does not allow to exploit full voltage span of the DAC. The attainable signal reach could be probably higher with a different module design. Nevertheless, the capabilities of the module presented here are sufficient to test the array forth code of the NFMIC system. And the array forth code is the following topic of my presentation. Basic NFMIC system presented here is composed of 10 nodes. It might be tiresome to present a full code for all nodes. Instead of making my audience falling asleep, I will demonstrate several short examples of increasing complexity, how the code execution and other techniques can be exploited to program GA chips in an efficient and elegant way. Of course, the examples to be presented are all excerpts from the NFMIC system code. First, I will show how a port execution by call is used to divide workload between 3 nodes of the reception path. Then the modulator at the end of transmission path will be discussed, and I will show how to control it using a port execution by jump. The last example shows how to start and stop the oscillator without direct access to the node 715 using a port execution of a code delivered with a ganglion message. Before we start with the first example, one important remark regarding suspended nodes. When a node is suspended, there are basically 2 ways of waking it up. Either by an external stimulus, if the node has access to a pin, at least a shared one, or by an activity at one of its ports. When suspended, while reading a port, the node may await some data, which will be processed by a code stored in the node's memory. Or it may expect the code to be executed out of that port. The distinction is crucial as the latter allows change the course of code execution within the node without the node even noticing that if some precautions are observed. The first example shows a port execution used in a cluster of nodes at the beginning of the receiver path. As explained earlier, the node 614 controls the execution of code in nodes 714 and 713. The keyword in the node 614 is run. This word is executed when a data frame is expected. The first thing the word run takes care of is to prepare the whole cluster for reception. It starts with sending the B register to down port, which is the port shared with the node 714. Then it writes 1200D hex into the port. The almost cryptic number is a hex representation of an instruction word for a call to the address 0D hex. Thus, the node 614 wants the node 714 to start execute a code there. The boot descriptor of the node 714, this is a code that describes the out of recent state of a node, stores the left port address into the A register, and the down port address, this is the address of a port shared with the node 614, into its instruction pointer. Thus the node 714 starts suspended, waiting for a code to be executed from its down port. And we know it's a call to the word pre. The word pre does some preparatory work, part of which is calibration of the ADC in the node 713. To this end, it writes 12019 hex into the left port. You may already guess that the number written to the port is a call instruction to the address 19 hex in the node 713. Also expectedly, a boot descriptor of the node 713 sets its instruction pointer to the left port. Thus, the node 713 starts execution of the word call. The word call first calls VSS to set an ADC to a negative supply voltage and then determines a count corresponding to that voltage. Then the word send writes the determined count back to the left port. This is the exact moment that the suspended node 714 wakes up and reads the value measured. The execution in 713 then returns to the left port and the node suspends again. Before the word pre in the node 714 comes to its end, it sends some data to the node 614 and then returns to the down port execution and suspense. The example just shown demonstrates the simplest use of a port execution. It allows to distribute complex code between several nodes. In a way, it's just ordinary factoring commonly used in fourth, with the difference that here we don't factor into words only. We factor the code out of a node into another one. The principle is the same. To sum it up, the port execution by call is the simplest method available. As it uses a call instruction, it pushes the return stack. Also, the word involved in the target node must end with a return instruction. Although the port execution by call is suitable for almost all situations, there are moments when it cannot be used. The problem with this technique is that it affects the return stack of the target node. An alternative is a port execution by jump. This method is used in the second code example, showing an implementation of an amplitude shift key modulator in the node 717. A boot descriptor of the node 717 sets the instruction pointer to 0. Therefore, the node starts execution from the word init right out of the reset. The code pushes 9 times a number 63 on the return stack and then jumps to the address of the right port. This is the port shared with the node 716 and suspends. In order to understand the meaning of the word init, I need to explain two concepts related to the F18 computer internals. Similarly to the parameter stack, the return stack has a circular design. There are 8 positions on the stack plus one top item in the register R. Pushing a value into the register R pushes its original contents onto the stack and discards the original bottom item. Pulling a value out of the register R pulls the value from the stack into the register, and at the same time it makes its copy into the bottom of the return stack. Another concept to be clarified is the for next loop. The word for is an array forth directive that compiles an instruction push and then it executes a word begin in order to mark the return address of the loop. Thus, when the loop is about to start, the top item of the parameter stack, this is the register T, is stored into the register R and the return stack is pushed down. The word next tests register R, and if the value is equal to 0, it is pulled out of the return stack, discarded, and the execution continues with the next instruction word. Otherwise, it increments the value in the register R and jumps back past the push instruction. Now, notice what happens with a return stack fully prefilled with the same number. At the end of the loop, the stack is restored to its original state. Therefore, with a pre-filled return stack, we can execute for next loops repeatedly without the need to push the loop parameter on the return stack each time the loop is entered. The source code for the loop is then a simple begin next clause. Let's return to the modulator code in the node 717. The two words that take care of its signal generation are mark and space. The word mark performs 64 cycles, where in each cycle it sets the DAC output to a predefined voltage and then to the ground. The switching of the analog output levels is controlled by a level change on the pin 17, which is internally shared with the node 715 running an oscillator. Thus, a carrier signal is generated. The word space works in the same way, except that it sets the analog output always to the ground. Combining marks and spaces creates the NFMIC signal. Now, notice the last instruction in words mark and space. It is a jump to the right port. Therefore, whichever word is executed in the node 717, eventually it jumps to the right port. Why? Well, in order to wait for a code from the node 716. The node 716's boot descriptor sets the register B to point to the right port. Therefore, whatever is stored through the register B is delivered to the node 717 and executed there. The two words taking care of this task are tick mark and tick space. The numbers set to the right port by these two words are hex representations of the jump instruction to addresses A hex and F hex the addresses where the words mark and space are stored in the node 717's memory. Why don't we use a call instruction? Recall that executing the call instruction at the port first pushes the address of the port onto the return stack of the target node. However, we need to keep the return stack intact as there is a loop parameter. Executing a jump instruction circumvents this problem on the expense of an additional instruction word at the end of mark and space, jump instruction back to the right port. When transmitting a frame, the node 716 receives a stream of bits, converts it into marks and spaces using the BMC algorithm, and instructs the node 717 to transmit them by jumping to the respective code through the port execution. While the mark or space is being transmitted, the node 716 has enough time to encode another bit in the stream and waits suspended until the node 717 jumps back to the right port, which immediately starts another execution of either mark or space word in the node 717. Owing to this design, there are no delays between marks and spaces transmitted. To sum it up, use the port execution by jump each time you need to avoid shuffling the return stack of the target node. Keep in mind, however, that the code executed in the target node must end with a jump to the port used for a code execution. Both variants of port execution, though useful as such, run eventually only a code stored in the target node's RAM. It only helps factoring the complex code into several nodes. Hence, the next example will show how to make a node run a code that is not stored in its own RAM. Instead, it will be delivered as a ganglion message. Before presenting the example, I'm going to describe shortly what a ganglion message is and how it is structured. The ganglion message is a means of communication between a polyphonic virtual machine and any other node of the G144 chip. When the message is delivered to a target node's port, it has two parts. The first one is a focus call to the port a message is being delivered to in order to get an exclusive attention of the node. As the execution address is that of the port, the instruction pointer is not incremented and the next instruction to be executed will be read from the same port. The second part of the message is a payload, which are instruction words and data to be processed by the target node. When the last word is delivered, Ganglia waits for at least one word of reply from the target node. Now, the oscillator node 715 starts execution out of the reset from the word go as is defined in its boot descriptor. It attempts to read the down port and suspends. In order to start the oscillator, it is sufficient to write one arbitrary word to the down port. The value is not important, but it allows the code to continue execution with the word clank. This word tries to drive the quartz crystal with pulses of different width and strives to find a resonant frequency. If not successful, it returns a non-zero value, hence passing through the if statement and writes a zero back to the port. The last action is to jump again to the word go. On the other hand, when finding the resonant frequency successfully, a zero is returned and the code continues past the dead statement. Drops the flag and returns a non-zero value that corresponds to the width of the driving pulse. The execution then goes on, some preparatory work is done, and it eventually arrives at the word run. This is an endless loop that drives the crystal to keep it oscillating. At the end of each cycle, it tests the down port to see if we want to write there, and if so, it reads the word from the port, sends the word back, and jumps to go, which effectively stops the oscillator. The reason for sending the received word back is that the protocol for the oscillator control have to be the same whether starting or stopping it. One word written to the port and one word read back. The architecture of the NFMIC system does not allow a direct access to the oscillator node 715. As you will see shortly, port execution is an elegant way to solve this problem. The boot descriptor of the node 615 makes it to start execution at the word start, which after some initialization ends up attempting to execute from the up port and suspense. This allows to start any code inside the node's memory using a port execution by call. For instance, a code that assures transmission of data until the end of data signal is written to the port. However, it also gives us an opportunity to provide any other code from the outside of the node to be executed at the port. Not surprisingly, the code is delivered by a ganglion message. The message is presented as a source code here, including the focus call. Each part, separated by a slash, is compiled as a single 18-bit word. Green words are array-forced instructions. The white word is a placeholder for a port address. The instruction pointer, as well as the current content of the port, are indicated for the sake of clarity. When executed, the code does the following actions. Fetch a word from the up port, that is, fetch the down port address and push it on the parameter stack. Store the address into the register A. Write any word from the parameter stack to the address pointed to by the register A, that is to the down port. Fetch from the same address. Write the word just fetched to the port the code is executing from, that is to the up port. Return to where you started from, which means return to the up port execution and suspend. As you can see, the node 615 performed all the actions needed to start or stop the oscillator. It has to be noted that the code is using both register A and parameter stack of the node 615 destructively and modify because it does not harm the rest of the code used by the node. It's obvious that in other situations we would need to take some precautions not to disturb the state of the node. For instance, we would first store the contents of the register A on the parameter stack before using the register and then restore it before leaving. To sum it up, the port execution of a code delivered from the outside of a node, either via a ganglion message or supplied by a neighbor node, provides an extreme flexibility to GA chip programming. The code delivered by a ganglion message must end with a return instruction, and it must send at least one word back. I would also like to emphasize that the port execution of an external code is one of the methods how to deal with often criticized lack of memory in GA144. Actually, there's really no need for more RAM in a node, as the length of the code executed at a port can be practically limitless. A very nice example of a port execution is shown in a green arrays application brief number 4. Probably the most elegant port execution example I've seen so far is a code used in the Polyforce virtual machine for communication between the main processing nodes and coprocessors. I strongly suggest to read the chapter 2 of the product data book. In order to show how the NFMIC system works, I have the code in Polyforce sends in 1 second intervals a word of data to the transmitter using a ganglion message. Words delivered by the receiver are moved through while node to the node 500. The code in the node 500 waits for a data word followed by an end of the data signal with all but sign bits equal to 0. Such a sequence represents data with a correct CRC. The GPIO pin of the node 500 is connected to a piezo buzzer. A simple code in the node 500 generates a beep whenever correct data is received. When an incorrect data is received, either with corrupted CRC or due to an interruption of the transmission in the middle of a message, no beep is generated. In the following experiments, the audio signal proves a correct NFMIC link between the transmitter and the receiver under different conditions. The receiver module lays on the desk while the transmitter module can be moved. It It is wrapped into plastic foil in order to avoid any short contact. I place the transmitter in the proximity of the receiver and start the application. Beeps are clearly audible.
I can hear him. Can you guys hear him?
I can hear.
Okay, good.
When moving the transmitter module far from the receiver, somewhere around 2 inches, the signal stops. Moving the modules closer to each other restarts the beeps. The second example shows how the magnetic near field penetrates also a human body. Even if I place the transmitter module in my closed palm, the signal is still audible. The last example demonstrates how the near field can penetrate metals. Although I have wrapped the transmitter module into a piece of aluminum foil, the signal can still reach the receiver. This is a clear advantage of using the NFMIC in comparison with other RF-based communication systems, for instance Bluetooth. And this is the end of my presentation. I wish to express my acknowledgement to Green Arrays people and thank you for your attention.
Yeah.
In the following presentation, I'm going to talk.
I have not got your email.
Should have just got nothing.
Okay, getting my mouse back. Okay. I got two, but they're both YouTube addresses. Sorry, Dennis.
Yeah, that's still not good. I just sent you another one. Can you pull up Chrome? Yes.
Yes.
Pull up Chrome.
Oh, I was in Chrome already, wasn't I? Yeah, I've got two copies of Chrome right now. Okay, that's all right.
Now go to plus.
Go to plus. What do you mean go to plus?
Plus.google.com. Plus.google.com.
Oh, you mean write it here?
Yeah.
Sorry. Plus.
No. Plus.
Oh, you mean spell it. Plus, and then Google.
There you go. Google.com. No, the one down here. Yeah. Here.
That one?
Yeah.
Okay. Now you see all the stuff I look at.
Now,
yeah.
go over to notifications. See if you've got a
There?
notification.
Okay. All kind of.
No, don't.
Sorry. Yeah. So, bring your computer over here. Sorry. Okay, we're going to have to. Actually, do we know that Daniel is paying? Okay. Hi, Daniel. We're trying to get it so you can actually talk to us and we can hear you.
Hi, can you hear
I'm
me?
guessing you can hear me.
Yes.
And thank you very much for that presentation.
Thank you.
Did I mention Daniel's in the Czech Republic? I think it's about 11 p.m. there. He's staying up late to help us today.
Correct.
And Dennis is going to move his equipment over here so that we can get Daniel up on the screen in the Google Hangout. And you can hope somebody has some questions. Think hard about a question. Otherwise, this is a waste of time. Now, can I, you're going to take this anyway, right? Okay. And then when you're done, we'll hand it over to Mangpo and company.
Wrong one.
Oh, really? Yeah.
doing this, I'd like to thank Dennis for maintaining the website. I know that you're all here in person, but for those of you who have not paid attention today, for posterity, this will all be on YouTube tomorrow and a week from now until YouTube. All where you're watching. I'm sorry, people are already watching.
Anything wrong?
I was just looking at the morning session. And, this is something back really cool if you have so Google Plus hang out.
Yeah, I won't go that far. Yeah.
Initial goal while we're standing here with you, how many of you plan to come to Bay and join us for dinner? 10 will make it. But keep your hands up because they'd like to count each individual one of you. We'll take another poll a little bit later, so we can call the restaurant.
Yes. Can you say something, Daniel? So we'll see if we can hear you.
I will. I'm saying something. Hello. Hello. Can you hear me?
Beautiful. We hear you. Thank you.
Okay. Thank you very much.
Anybody have a question for Daniel? Please have a question.
How's
Peter.
the weather there? Come over and use the microphone.
Okay. Do you think? Okay, Peter, what do you have to say?
So thanks for your presentation. What's the accuracy that you're timing the signals? And it's a more general question about the timing accuracy you can get.
Well, the signal.
Interesting.
It's a small clock crystal. So the accuracy, I don't know by heart, but nothing special, I would say. And if you mean the data bits sent over the carrier, well, then the accuracy is limited by the asynchronous nature of the GA144.
Mm-hmm.
But as I explained, there's really enough space for any non-accuracy in the width of the bit. It's quite robust, the system.
So it's accurate enough.
Yeah.
Any other questions? Come on, after all this trouble getting it set up, we got to have another question.
Another question. Thank you for the.
Yeah, Daniel, this is John Ribel speaking.
Okay.
Thank you for the examples.
Thank you.
Yeah, I love those examples. I need to learn how to do as well as you're doing because I actually feel like I learned something from it. So thank you.
Oh, thank you very much.
Dave.
Thanks for your presentation. I just wanted to know what some of the proposed applications for this device might be.
That's a good question.
Okay. I don't want to mention any company's name, but there is in US there is a company that actually uses this system to how to say, it's used in army to have an inventory of guns in a warehouse, simply said. So each gun has a transceiver, and there's a module that's simply asking how many guns is there, and they answer. And if you move the gun out of the room, it simply detect that. And the advantage is, as I shown, that the guns are made of metal, but it doesn't matter for the system. Obviously, this commercial application has a higher or longer reach than my module, but the principle is the same. And I think there are other companies using that, but it has not been very much published, I think, for commercial reasons.
Mm-hmm.
But the standard I mentioned, IEEE standard, is available, and it describes pretty well how this works, so I could use it. And I know that similar system is used in, I don't know exactly where, but for policemen, they have a radio, and microphone is not connected with a cable, but there is this NFMIC link. So it's better for movement. There's no cable hanging on the guy.
Yeah.
And I personally started with this project because I have had an intention to use this system for smart sensors applied to the human body, or for instance, it can be on the body or how you say that, installed into the body, just to check, for instance, heart rate or things like that, and that has to communicate. So it's not harmful to human body, this kind of communication, and it can pass through the body. So these are the advantages.
Sounds good. Question?
What's a reasonable range between the transmitter and receiver?
Based on what I know from literature, it's between decimeters up to few meters. The system used for the guns I mentioned, they have reached several tens of meters, but there I think they use higher power or something like that.
Mm-hmm. So it's near field. The near is an important word.
Yeah, definitely. I would be happy if I had a module with the reach, let's say 1 meter. That would be great for my purpose.
Yeah. Anybody else? Question? Yes, one more.
What power would be required to reach a meter? What are you talking about as to power level?
Do you know?
Frankly, I have no idea. The intention here was to use 1.8 volt available at the evaluation board, because at the end of the day, the sensor will be very small, and it has to be really considerate regarding the power used or energy used.
Mm-hmm. Energy, right?
So, so that's one thing, and very likely the analog part of the module, it's something I just tried and it worked, but this is not really good design, and I'm not really hardware guy, and absolutely I don't understand analog circuits, so I'm actually looking for somebody who would be willing to help me with that. So if you're interested, or anybody there, happy to cooperate with somebody. But the intention is to use the same voltage as available for the chip. It's 1.8 volt.
Okay. Thank you, Daniel. Another question.
Just another. Have you tried any of this through water? There was a mention about this will work through water.
No, actually, I wanted to do that, but due to the lack of time, I haven't. And I haven't prepared, but actually I'm going to try, because it should work. It should work.
I've heard.
5 minutes.
I saw something like this done around 1978.
Could you repeat your question or comment?
Sorry, coming back. Here I come.
Now I need to say that I saw something like this happen around 1978, 79. Where a guy was transmitting his business card with a handshake. So, old idea, new implementation.
I have to find that. I know that the system, from time to time, I find a publication where they use it, for instance, with miners, because to transmit radio signal through when they are underground, it's difficult. So they try to use this system.
Bob,
there are several applications that could be found.
Yes, Bob.
This isn't a question so much, but it's information. I believe a fellow named Dave Johnson on the web has circuits, and I believe he had some circuits for communicating at this frequency. I think he had large loops and walls or something. I'm not quite sure, but he's quite approachable. I've called him several times. You might want to look at his circuits on the web. You were talking about analog circuit help.
Okay.
If you're interested, I'll get the pointer from Bob and send it to you, okay, Daniel?
Okay.
Then you don't have to remember that name.
That
Okay, Bob?
would be great. Yeah. Thank you very much.
Okay. Anybody else? Anybody else have anything to say? Thank you very much, Daniel. I really enjoyed it, and it's a pleasure having you here.
Thank you.
Mm-hmm.
At least like that. I thought I will come in person, but not this year. Maybe next time.
I hope that, yeah, I'm looking forward to meeting you in person.
Thank you. Okay.
Okay, next speaker. Thank you, Daniel.
Bye-bye.
You guys, yeah. And I'm going to hand this, well, let me introduce you. I guess I mentioned briefly, we have a couple of students from UC Berkeley, Mengpo and Michael. And I'm sorry, like I said, I don't know how to pronounce your last name. And I don't know, okay. They've done a project, or extended a project, using the GA144, which of course is the green erase chip. So, who's going to speak first? I'm going to hand the microphone over to you.
Okay.
And this needs to be clipped because it makes a lot of noise. Yeah.
Okay, it works. Yes, hopefully. Okay. Hi, my name is Mengpo. I am a PhD student at UC Berkeley, and I think some of you have heard about my project before because I presented about this one 2 years ago. So I'm gonna give you a review of what I have built. So essentially, I built this chlorophyll compiler, which is a compiler that compiles from high-level language, essentially a subset of C down to array 4 that can run on green arrays. So I'm gonna give you an overview of the compiler, and then I'm gonna hand over to Michael. He's an undergrad who worked with me at UC Berkeley, and he's gonna talk more about using the compiler that I built to actually build an application that run on green arrays, and he also extend the compiler and also build some tool chains to make it work with green arrays. So we're gonna start from the compiler itself first. So essentially, compiling for green array is not easy, and we require new idea than just using traditional compiler techniques. So we introduced this technique called synthesis-aided compiler. So let's take a look what that actually means first. So classic compiler, I think maybe some of you have built some sort of compiler before, but the idea is that in order to compile from high-level language down to the machine code, what you do is that you have to introduce a sequence of transformation, right, that goes from high-level language down to the machine code. You also add optimization passes so that you generate optimized code. But for a lot of machine code, you require a lot of effort and thinking of how to actually generate really optimized code, and especially how to generate code that fit in each tiny core of green arrays. That's not easy. So instead of using these classical compiler techniques that require a lot of thinking of how to come up with this sequence of transformation, what we do is that we use what we call program synthesis. What it means is that instead of coming up with a sequence transformation, we basically define the search space. So essentially, that big cloud over there is the search space of all possible programs. And you have an input specification, which could be a high-level language program. And then you try to find a program in that big search space that is equivalent to the input specification. But of course, if you do this naively, you're going to take forever to actually find program that equivalent to your input specification. So we need more clever techniques. So the way that we approach this problem is that we first divide our compiler into 4 stages. The first one, we do partitioner, where it takes in high-level language, which is a subset of C, and then it will partition program such that each partition would fit in each green array node. And it will partition in such a way that it will try to minimize the number of messages sending between nodes. And then after that, we get a logical core. And then the second step, we map logical cores to the physical cores. And then after that, we actually separate code into multiple pieces. And for each piece, we actually generate the array-forth machine code. So let's take a look at the high-level program that we have, which is a subset of C. So here's a really simple example. We provide this optional, we'll call partition type, so people can annotate the program. So in this particular example, what it means is that you actually tell the compiler that you want to place variable A and B in node 1, and then you want to place the variable ands in node 3. You can also tell the compiler that, okay, for the multiplication, I want it to be in node 2. So you can see here with this code, the compiler would automatically generate this communication between node 1 to node 2 and send the result to save in node 3. Okay, and of course, you might not know how to write those partition annotation by yourself. So what you do is that you can partially specify that in the programs, and then you let the compiler come up with the partition annotation for the entire thing. So we use our partitioner, which is a constraint solver, that try to come up with partitions for all the variables and operation in the program, such that it will try to minimize the number of messages sending between cores, and it makes sure that the code will actually fit in each tiny core. All right, and then I'm going to skip to the last part, which is generating array-forth code. So what we do is that instead of doing the sequence of transformation and generate the machine code like a classical compiler, we just have a naive code generation, which is fairly simple. It just translates our IR to array-forth, but it's not very efficient and it can produce really big code. But what we do is that we run that through what we call super optimizer, which is essentially searching through the space and try to find an equivalent sequence of array-forth code that equivalent to our generate code. And it actually surprisingly finds something much smaller than what generated from the naive code generation. So with that, we have some results where we actually write an MD5 hash function using in chlorophyll, and then our generated code is only 19% slower than Charlie's code, which is actually not bad at all. But but the very interesting part is that actually in 3 functions in that MD5 implementation, we actually found shorter codes than Charlie's code. So you can see here, these are what Charlie's implement in his MD5, and our super optimizer actually found something shorter. So we can also use our super optimizer to optimize on like handwritten code and get something better too. Okay, so that's the nutshell about the compiler, and now I'm gonna hand over to Michael to talk about application he built on top of this.
Uh-oh.
La-di-da. There you go.
Oh yeah, this is Ubuntu does this like yeah. How do I?
You can also. There should be maybe that one.
Display the thing. Ah, cool. How do I present? Okay. So first going to talk a bit about alternative array forth tool chain that I built to kind of make my life a little easier. And then an application we're working on, a gesture recognition on GA144. Some chlorophyll modifications that we had to do to be able to enable that. And a bit of work on the sensor tag application, and I can demo the code. So, an alternative tool chain. Compiler, bootstreamer, simulator. It supports most of array forth. Everything that's been relevant that I've needed, there's some things that aren't touched on. The big motivation for this is really this having to these little manual compilation steps that I have to do every time that I compile code, want to run on G144, I have to convert it into this color forth format and then load it up, manually edit some code with the correct addresses once it's been compiled, and then load it. And that gets, for me, it's pretty tiresome and kind of takes away some of the fun of this whole chip. And so the compiler, this started from just as close as it could to array forth, and because I'm the only one using it and I have all the control, things have kind of started to diverge a little bit. Obviously no semantic color, address literals, ampersand in front of the word name compiles a literal call, or just a literal word address, automatic knob insertion. That's kind of suboptimal. Lots of times you don't really need them. It throws them in all the time. Automatically resolves northeast, southwest to the port addresses in whichever node it's in. Can resolve forward word references. One difference is all the words and all the nodes are in separate namespaces. So if you want to compile a call to another node, if you're going to do port execution or something like that, you can reference it with the word at node syntax. Of course, there's a Emacs mode. Every language needs an Emacs mode. So things like doing generalized host computations during compilation, that's not supported at all. I haven't needed it. Maybe in the future. Bootstreamer generates async boot streams or 2-wire and can support streaming programs into the host chip through the target chip. And yeah, no support for boot descriptors I haven't needed yet. Yeah, and the simulator, this is probably the least useful to anyone else because I'm the only one that's used it. And the interface is kind of rough. But it enables a few things that you can't really do with the current one. Like there's unlimited breakpoints. You can break on words and also line numbers. And yeah, break on IO pin changes. No support for lots of IO things, phantom wake-up signals, SerDes, stuff like that. And you can wire multiple chips together and simulate them all at the same time. And yeah, so onto the this application that we've been working towards is doing gesture recognition using hidden Markov models. So the training is initially done on my laptop, and these models, which take about 4 words each, are loaded with the code into the chip. So we're not using SRAM or anything. We're a little limited with the number of models we can, a number of gestures we can classify, but it should still be interesting. Because we normally, all of these classification programs that I've seen have loaded up, have taken a sequence of data and have then done classification on that, but we don't have any room in the chip to store a whole accelerometer sequence for a gesture. So we stream it in one at a time. After each gesture is read, we increment that's the standard forward step procedure for this. One increment each time, it saves the state in between readings, and so we can do it in constant memory space. this is what it will look like. Each one of these boxes with the dots is going to be another gesture. They're all going to run in parallel. After some start or stop condition, probably with buttons, we're going to read the accelerometer values, filter them out. So it's like directional equivalent filters and idle state, and then distribute that reading to all the gestures, be quantized, and another step in the forward procedure will be taken. At the end, it's going to choose the best one of those, reset all the models, and report the gesture. So in doing this, to read the accelerometer, we have to implement I²C, which has kind of brought up some problems with the way that chlorophyll is compiling code, because there's so many digital, or so many IO functions that all have to be crammed into this node. In particular, 708 is a problem node. We just can't fit all the code in there. It generates too much communication code to keep everything synchronized. It wasn't doing any port execution. So I think problems like that are probably to be expected. And so what we've come up with is, we kind of think of them as actors. We're basically taking, we're separating code into groups, putting them into nodes, putting those nodes into port execution, and we send executable words. So we think of those functions in the port executing node as the actors, and the executable words as messages that we send to them. And so right now we have to explicitly declare which nodes are going to be, or which functions are going to be our actors. And so it's an example of the reaccelerometer function. And so this will reside in partition 7 and will be called from partition 8. In the future, we think it can be possible to kind of automatically find these, or just leave this as an option, kind of like in the way that partitions are optionally specified now. And so this was, the first thing I did was kind of like re-implement the sensor tag application in chlorophyll. This is from Green Area's application note 12. There are some changes. So like the basics of this is that there's this TI sensor tag. It's like a little board with 8 sensors on it, and it communicates to a little processor with Bluetooth over an I²C bus. And we cut that bus into 2 and put the Green Array's chip in between them. And so we can talk to all the sensors on one side and then the Bluetooth on the other side. We are just talking to the sensors. Instead of Bluetooth, I have it going, communicating through serial through node 600 instead. I forgot a node here. Node 708 actually does timing for I²C, and 713 does timing for reading, like once a second or something like that. So these functionalities are kind of pinned there because of the IO nodes or the pins that they use, but everything else is kind of like in that cloud. Like that's not, we don't really concern ourselves with where that ends up. Chlorophyll fills that in. This little example of this is the code that finds the crystal resonant frequency and maintains oscillations by pumping the crystal. The code in the array forth on the left is not, that is the, that's from the sensor tag application. It's not generated, unfortunately. And it's chlorophyll on the right. You can see the IO functions that we had to add. Set IO, digital read, digital wake up.
Right with that?
Oh yeah, well, yeah, you can see them. So, yeah, it's all online. If you want to use the code, the compiler and the loader that I wrote, you should wait a day or two so I can write documentation. There is literally nothing online about it. and I think I might have missed a few files and pushing stuff. So, yeah, I haven't told anyone else about this before now. Now that I have, I'll get on that. Yeah. So, oh yeah.
So the first link is to the compiler, the call-through compiler that generates from subset of C to array 4, and then the later one is the one he talks about. It's like the tool chain to load everything, like debugger and everything.
So yeah, I can give you guys a quick demo now of what that's like.
We're still working.
Yeah, maybe. Let's see. So first, yeah, the simplest in Node 708, we're going to do. This is code for serial communication, and then the Lucas series, and run that. I haven't added myself to the dialog group yet, so I need to run it as sudo. You shouldn't have to do that. So yeah, that's it. Compile, load, run. I can do the sensor tag app. So here we load it on the code. The boot stream gets loaded into the host chip and gets loaded up through that into the target chip, and that's through the USB-A port on the board, and then the host, the target chip sends the results, the readings out through port C. So first need to run the script to listen, and then we can load the code. No. Yeah.
You can unplug and try again one more time.
Okay. It works.
See? Isn't that great?
Yeah, it's I don't know. We've been having problems with that recently. But you know the old trick, you just turn it off and turn it back on again. Yeah. So this is the green array sensor tag app that I took out, and am using the new compiler for. So yeah, that works. And now the last one is the chlorophyll that reads the accelerometer values. Gonna hide those error messages. Okay. Yeah, so there, it's the last three values, X, Y, Z. Just the raw values are not converted or anything, straight from the bus.
And is the accelerometer on the board as you move it?
Yeah.
Yeah, so it's
So,
that particular one, that
Right.
component. Yep.
So you see the stuff change as you move it around.
yeah, it doesn't really make sense right now. You can't really.
You have to like
but you
convert the
get-
value.
You get
He's
the
moving it, the numbers changed.
Yeah, and then they kind of change back. Yeah. So yeah, I'm afraid to move it too much, but.
What about the sensor? You're measuring. What about the sensor on the table? That's I don't know what is it? Ultrasound?
By the way, the people on the internet can't hear what you're saying, John.
That's all right, but you can repeat.
Okay.
We
The
can
other thing
repeat the
was-
question.
What you've got plugged in
Yeah.
over here on the table.
Yes, this.
Keep going.
He asked what are they?
What is that?
This thing.
No, repeat
This?
the question
Oh.
for the internet and then answer it.
Oh, never mind. I thought that the box on the table was plugged in, and it's not.
Nope.
Oh.
Okay. Yeah. No.
Not
Red
that
herring.
much.
Yeah. No. It's just the sensor tag board on the eval board.
Right.
Cool.
So are you taking questions now?
Yeah.
I have one.
Questions? Mhm.
You have to speak
Is
up.
yeah, is color forth involved at all in what you just showed us?
Well, the Emacs mode has colors in it.
No, I mean, I mean it. Did you come up with your own packet that you sent through the serial port, and you didn't have to use the ColorForth IDE or any of that kind of stuff?
Yeah,
it's all Linux.
So I can show you like this Lucas series example. Let me run that again. No, that's the wrong.
I think you've already answered my question.
Right.
You've basically
That's Lucas
recreated
series.
all those things.
And then if we want to like fool around with it and change some values in here, we can change that, save it, recompile it, and then see what goes on. So yeah, it's completely independent of Green Array tools.
All right. That was the question.
And it's meant, yeah, if you're in Linux, it's, I don't know, and you like to work that way.
Downloading it right there.
Yeah, so you can.
So that codes actually like run on Green Arrays and it print out that data and send it back to the computer. If that's not clear, so that's what's happening.
So if you want like
say that a little more slowly, a little more close to the microphone.
Like what I have to say.
Yeah.
Yeah, talk to Michael.
Oh, I was just saying that like the process that my codes did was actually like compile everything, run on Green Arrays, and then it print out numbers and send it back to the computer.
Yeah. Well, you're going to say run on Green Arrays. You mean on the hardware?
On the hardware,
not
yes.
ArrayForth.
Yeah, that script, it compiles, it loads it, and then it automatically, unless you tell it not, it goes into like a listen mode. And so I also have another script that you can kind of dump the results out. So for this application, it's node 608 and 607. You can see how many words it used. You can also just dump everything out. When it's compiled, when it's assembled, if you want the boot stream, that's the boot stream. You can also put the symbols in there. If you want to know where the symbols are, if you're doing, that's used by the simulator, the interpreter, if you want to set breakpoints for words. Yeah, so.
I think that's pretty cool.
Other question? Or you have to walk away.
Oh.
Yeah. Oh, wait.
Should we just repeat it?
Yeah. Is it free? Can they just repeat it? Yeah, you want to clip it to your garment or it's not going to be a screen.
We don't think so.
You have to clip it to your garment or they're not going to understand what you're saying.
Okay. You got to clip it. Go ahead. Here, let me clip it, because I'll forget what my question is. Your program chlorophyll, basically what you're saying is can take C and translate it to fourth. Now, can that be any fourth? You know, ANSI fourth, you know, Joe Blow's fourth. Can that be, is that possible?
Right now, it only worked with ArrayForth because I made the back end only generate ArrayForth. It is possible that it can generate other kind of forth, but we have to change the compiler to target different kind of forth.
Right. Because what you're generating literally is machine code.
Yeah, although like the machine code is just ArrayForth, which is
It's ArrayForth.
yeah.
Well, another thing, you're not really doing C. It's a subset. It's a subset and a modification of C.
Right. So like what we support right now is only a subset of C, so we don't deal with pointers because it's very hard.
So
Yes.
it's neither of those things you're asking.
Okay, that's why I just wanted to get that clear.
Other question?
Michael, I'd love to see that Emacs mode sometime. Are you going to share that too? In some way?
Yeah, it's on the repository as well.
Okay, great. That looks really interesting.
It's pretty basic right now, but
That's good. I need
it just colors stuff, which is nice.
That's all I want.
Yeah.
Thanks.
Thanks, guys.
Thank you, Mengpo and Michael, very much. And it's going to be a minute or two while I get set up again. Okay. Are we ready to go, Dennis? Is that all right? Okay, thank you. I'm Charlie Shattuck again from Green Arrays. The job I was assigned a while back, sort of a crazy job, and you guys can, laugh or whatever, but I was given the job of making a C compiler for a virtual machine running on the Green Arrays chip, or the evaluation board. I think that we thought of it as largely a marketing idea rather than the idea of making something better than what we already have, because obviously everyone at Green Arrays is pretty happy programming in Forth, and it would be pretty insane to say that we really want a C compiler for this machine for ourselves. But we know that there's a lot of people out there who think they need C compilers, and we'd like to encourage them to look at us. And then, of course, after they get into it, they're probably going to see, wait, so much easier in Forth. What am I doing? Maybe that'll work, maybe it won't. But for a while, I was working on this by myself. Greg Bailey assigned it to me as my job for a while, and I didn't want to do it because I didn't understand C enough to begin with, and I didn't think I was going to do a good job, so I did a horrible job. And I was really not proud of what I was doing. But some of you know Stefan Mauerhofer. He's spoken here a couple of times, maybe only once here, but anyway, he's done a couple of app notes for Green Arrays, and he's worked with us quite a bit. He's actually a C++ programmer over in Switzerland. He may well be listening right now too, so if you are, hi Stefan. Stefan, like I said, is an expert in C, and he explained the whole C virtual machine to me in a way that made me think that using C wasn't absolutely and totally insane like I used to think. Now I just think it's really different. And I can see a few things that are sort of mildly advantageous, but I'm never going to switch. I know forward and backward, and I think that way. So the bottom line is, it's a good thing that Stefan came on the job, because he and I worked together. He was here in America. Yeah, he was at my house in Roseville. I think it was in May, just before the summer, for a few days. We brainstormed on how we might want to do a virtual machine for a C compiler. While he explained, all about stack frames and parameters and local variables and how the stack frame points at those things. Things that were a complete mystery to me before. And we came up with a bunch of crazy ideas in our brainstorming. He went back to Switzerland, and we started trading back and forth things in the email. Finally, I just decided, why don't I just go look at what Bill Mensch and John Reibel did in Polyforth and see if I can't just copy that, or extend it. And what they did was, I would say, absolute genius. It's a work of art, and I highly recommend everybody should go read the source code and the documentation for the Polyforth virtual machine. Well, they did the eForth virtual machine, but they're essentially the same thing. It's a beautiful thing. So Stefan and I started basing our virtual machine on the Polyforth model. And we came, after a lot of iterations, basically we were having a contest for a while where I would try it, he would try it, and we'd compare. And finally, after not very long, I said, okay, you win, Stefan. We're going to just go with yours, and I'm going to start testing yours. So he refined his model of the C virtual machine, and I decided to get to work testing it. And we didn't have a C compiler. We only had a C virtual machine. So to do the testing, the first way we did it was in SoftSim in ArrayForth. And I would decide what codes I wanted to run. I'd look them up in the documentation. I'd write those numbers in with a comma, you know, hex numbers, and then run it. And that was really tedious. So I just decided to spend an hour or two making a assembler for the virtual machine. And I'm more comfortable in Gforth and Vim than I am in, say, Polyforth or ArrayForth. So that's the way I went. Basically, my assembler, which I'll show you a little bit more of in a minute, it's almost the same thing as what I did for the 8051 for my Forth, and then later I did my Forth for the Arduino, and it's all basically the same stuff, which I'll show you in a minute. But then I'd write codes, I'd put them in SoftSim and test them, and then I'd fix them and repeat. Well, I'd find a bug and I'd tell Stefan about it, and before I could even think about what might be wrong, he'd give me the answer and fix it for me. So the Polyforth model, here's a few details about it. Yeah. This is maybe the first time I ever remembered to bring my laser pointer, so I'm going to use it. There. There's a module in ArrayForth to drive in a driver for SRAM that uses 4 nodes down at the bottom of the chip. And the SRAM driver has 3 memory. Maybe I should show a different picture. Excuse me a second. I'm going to jump ahead because I have a nice model. The memory driver, it basically is these 4 nodes. The 7, 8, and 9 can have I/O pins that talk to an SRAM. 107 is in control, and it's called the memory master. But 107 has, well, let's see, it's called the memory interface. It has 3 neighbors that are memory masters, and each of these 106, 207, and whatever that is, 108. Thanks. That's how good I am at that sort of thing. Those are called memory masters, and they have access to the SRAM. They can read and write from SRAM, and the 107 polls them in such a way that they all can get at the SRAM as you need to. My point was, let me go back up here. The layout that Stefan came up with has 207 as the memory master, and that's the one that's right up on top of the memory interface. And this one, it has access to the stack pointer and memory real easily because fetch and store goes right out to its neighbor. I'm going to digress a tiny bit and say that the C virtual machine that Stefan described to me has a lot of registers in it. And they're distributed throughout these different nodes that we're using for the virtual machine. The program counter is 1 register. No, I can't point with this. And the stack pointer, those are 2 obvious things. You need to know where the next instruction is going to be in memory, and you need to have a pointer to the stack, and there's only 1 stack in C. There's also a frame pointer, though. It's like an extra stack pointer that'll point into the stack frame for a particular subroutine, and relative to that frame pointer, you can find your local variables or your parameters on your parameter list. But the frame pointer is not quite as important as P and S, so F is kept over here in a neighbor. And then we have the return value register. It's kept up here in the actual control node. This is the node that's in control. It feeds codes to the other the other nodes to tell them what to do. But and if you're going to fetch something from memory, this one tells this guy to do it, and he goes down and does it. So, well, the return value, I think of it a lot as like the top of stack, like T, except that it's not exactly, because you don't have to. It's really a loose version of T. You don't have to necessarily push it and pop it when you want to use it. You can ignore it. Anyway, at times. But any function in C is going to return a value in this register, the R register. So most of the virtual functions in this VM, like arithmetic and logic, they're going to, binary functions, they'll take one item off the top of the data stack and do the function with the return value, or the return register. It's like top of stack and return register. That's the only addressing mode for those kind of things. And then the answer is returned in the return register, whether you need it or not. There's a few other registers. There's G and N are called the global pointer and the new pointer. And global pointer is for global variables. And the new pointer is a pointer into the heap, which I haven't learned a lot about yet. I haven't used it at all yet. But I will find out. I'll tell you later. But yeah. Somebody out in the audience, John said malloc and free, but whatever. I'm going to learn those things later. We also have a D register over here. And this node 306 pretty much exclusively handles double or 32-bit arithmetic. I didn't mention this is a 16-bit model here. So integers are 16 bits. We're ignoring floating point like it doesn't exist at all. And but we are having double precision arithmetic, so you can do 32-bit arithmetic. And generally speaking, the bottom half of a 32-bit number is going to be in the R register, and the top half is going to be in the D register. And again, they're in separate nodes, but these nodes are cooperating wildly. Also, there's a 308 has a lot of compare instructions for when you want to branch based on comparisons. It also has a few more arithmetic things in it, but it also has a T register, a temporary register, and I will admit that I don't know what we do with that one yet, but that's where it is. Also, there's one over the node 407 has W and PT registers. We do I/O with the rest of the chip, yeah, from 407. And I haven't done much with this yet. Let's say I haven't done anything with this yet, but I understand how it's going to work, and I'm pretty soon now going to attach this node up to some ganglion and send out ganglion messages and do I/O outside of the chip. And we'll see how that goes. But the W register means the word register. It's an actual 18-bit register, and it'll have whatever word we're going to put out to a port. So it needs to be 18 bits. And the PT register is the port that we're going to be writing to. So it's either up, down, right, left, whichever. Well, let's see. It's one of these. So it's, yeah, I can't calculate. It's right and left, and it's either up or down, whichever that one is. Sorry. Thank you, John. John says it's up. John Rival. And I look at the chart every single time. I've got a chart over there. I could go look it up, but that's not my skill or my talent to remember that. Okay, let's see. Just for your information, each of these nodes is pretty much full. They're not. Some of them are full with 64 words of memory used. Some of them have maybe 8 words of memory left, or some of them have 1 or 2, but they're pretty full. They're used, so it takes that much to do Stefan's version of a C virtual machine. And just for comparison, eForth pretty much got away with 2 nodes, and the neighbor, the buds, were added in case you wanted to extend, but eForth didn't extend it at all, right? So eForth really fit into 2 nodes. Much simpler, you know, and you're not surprised, right? Forth is simpler. Polyforth is a little bit expanded. It has a few more things than eForth. So it has a few of these neighbor nodes with just a just a few words of code, not much, but But anytime we think of something we'd like to change in the layout, or not in layout, but in the instruction set, or if we see a bug in the instruction set, it's a really fun and interesting job to find the memory to fix it sometimes, because these are pretty full. I think that's enough of that. Also, if anybody wants to ask me a question in the middle, I'm kind of winging it anyway, so I wouldn't mind it. If you have something that I'm saying that sounds really stupid or you don't get it, feel free. This is an example of how I assembled my instructions. And it's a whole lot like what you've seen, mostly Bob Nash has talked about, my fourth. I wrote it a long time ago, but Bob has done a whole bunch of stuff with the 8051 version, and then now with the AVR version. It's kind of my hobby on the side, but mostly it's Bob that does it, and I help him. But basically, my target compiler is that right there. Not my target assembler. And it's extremely simple. I just make an image in memory someplace that's big enough. It's 128 times 1024, whatever that comes out to be. I don't even remember why I made it. Anyway, let's ignore numbers for a while, because I'm not good at winging numbers while I'm talking. I have a dictionary pointer. I have the word org, which can point to the someplace in the dictionary. I've got a lot, which can give me some space. I've got here, which returns the current location in the dictionary pointer. That's in target terms of memory. I've got there, which translates whatever my target address is into an actual address on the host, where I have it in a buffer. And then I have comma dash T, meaning comma it over there. Here, there, W store, one a lot. W store means in G4, at least in my 32-bit G4, it's a 16-bit store. I've got to figure out what it is for 64-bit, because Bob uses a 64-bit G4, and we have trouble sometimes. But anyway, that's pretty much it. All you need to do to target assemble fourth is have a way to comma stuff into a buffer somewhere. It's so amazingly simple. Then I have three different types of opcodes. Basically, the opcode that has no addressing mode whatsoever. And I have the ones that have access to the stack, and those have a field that has an offset into the stack. And then I have a different offset. I forget which instructions use that one, but there's a different offset for some of the, see, one of them has an extra bit in it. You can see the mask right there. And then I came up with the word function, where I can, it's like colon. But since it's C, I thought I'd use the word function. And now, that's pretty much the whole basis of a target assembler. Then I start making instructions. The instructions that fit the patterns, like these opcodes, like push and return, I just say the opcode, the hex number for the opcode, the word opcode, and then the name I want to give it. And I'm putting commas after all the names, because I remember years ago we used to do that in FIG fourth, and because I'm too lazy. I don't know if I'm too lazy. Whatever the reason is, I'm not using vocabulary. So I'm not using a special vocabulary. I'm just putting all this on top of fourth, which I may rethink, because every once in a while that causes trouble for my end user. And I noticed I said end user, Bob. Only one person. So I'm going to rethink that. But this is, to me, the simplest thing I could possibly do. No vocabularies, just put a few words on top of the main fourth vocabulary and come up with instructions. Some of the instructions are unique enough that I don't make a defining word for them. Call is the only one that masks off 15 bits, and plit2, which means push lit 2 and push lit by itself, they're different because they have 2 or 3. Wow, interesting. Oh yeah, 2 or 3 words instead of just one word. So I code those straight without a defining word. So this is just a few more. I've got more opcodes: push, return, exchange stack, exchange P. What these two instructions do is exchange the stack pointer and the return pointer. Yeah. And return doesn't mean return stack, it means the return value. So this one returns the program counter. I'm not going to go into all those, that would be crazy. But some of these opcodes are stack relative, have a stack offset in them, an offset field. So see, enter and exit, those are words for building and tearing down a stack frame. Not words, they're instructions because they're part of this machine, this virtual machine. Let's see. Anything that starts with ST is store and LD is load. What is L? Local. Store local, store parameter. So if I want to store some value that's already in the return register into the stack, let's see now, into the locals that I've allocated, like say the first local, I would say 0 store local, and it would take whatever's in return value register and put it in a stack in the right place. And that's enough of that too. I don't think you need to learn everything about this. And at the end of that file, after I've defined all the instructions, then I add the macros that makes this like a structured assembler, you might say. It has many of the conditionals you'd expect to see in Forth. But once again, they end with a comma to indicate that they're part of the assembler. And I don't have a Forth on top of this. This is just a way to test machine instructions. And it's just like this, every other Forth that I've learned about that uses, you know, structured conditionals. For begin, you just put the here on the stack is at compile time or assembly time. It stays there until again or whatever word it is that comes at the end needs to use it. And then, for example, again, it takes whatever was already on the stack, which was an absolute address, makes it a relative address, and commas in the branch instruction. And the branch instruction, as it was defined, puts that address into its address field. And that's enough of that. Entry comma just tells where the entry point to my program is. It stores it off in the reset vector, actually, which apparently is address 1. When I'm finally done with all that, I redefine comma dash T as comma so that in my source code I can use comma and it looks normal, because I don't really need to comma anything into the host anymore at this point. And then this is very important. I have a word that uses file words to save the buffer into a file so that whatever program I'm using to get it into the machine can get at it. And that's that. Let's see. Here's a quick example of a program that I wrote the test. I'm not showing you the breakpoint, but there's a function that I came up with called a breakpoint. And what breakpoint does is when you execute it, it carefully saves the return value, and it goes out and basically queries all the nodes to figure out what the registers are and puts them into an array in the global memory someplace where I can find it. And when it's done, it restores all those things. So having done the breakpoint, it's called break. I write a function called init, and it says entry. So entry says this is the program. This is the entry point for my C program. These lines, FF10 LLit means put a long literal into the return register. XS means exchange that with the stack pointer, and break. So what I did was I just loaded FF10 into the stack pointer, and break will break, and whatever program I'm looking at it with will theoretically go look at memory and see the location where I've stored the stack pointer and see, yep, FF10 got there. I'll show you that in a second. It goes on. And at the end, it just goes through breaking and decrementing the return value over and over so I can see that it's actually running. And this is just a super simple test program to see if my breakpoint thing worked. The things after that are just because I wanted my disassembler to show me that those were working properly. They're not really part of the program. This is array forth. In order to test those instructions, I tested them in SoftSim first, as Stefan wrote them. And I could see, SoftSim has a single stepper. I can go through and see where things go bad. I can see, you know, actually, I don't even need a single step. I can say go fast, and if it goes off and, you know, off nowhere, obviously something's wrong. So then I start single stepping and seeing what's going on and trying to figure out what's wrong. To make it easy for us, though, I modified SoftSim a little bit. So this is the picture that shows one node up close. It has a memory dump. It has a dump of both stacks. And part of the memory dump is a disassembler. So I added something similar that shows external memory, where I have all the registers shown over here. And they're easy to get at in SoftSim, not quite as easy to get at in hardware with the breakpoint. Over here, I have basically two memory displays. One is the relative to the frame pointer, because I think that's interesting with the locals and the parameters. And the second column there is relative to what, I'm sorry, that doesn't make a lot of sense. I'm gonna have to show you the real thing. Yeah, anyway, one of them is a stack and one of them is memory where you're executing code from. And to me, it's not obvious right now which is which. But here's this is though. Okay, now you guys know what an idiot I am. These are addresses, obviously. These are values. So those are on the stack. This batch, these are addresses again, and these are values which happen to be virtual machine instructions, and they're disassembled off to the right. The best I knew how. Some of them are kind of crazy because call is kind of hard to recognize. Sometimes, like plet, pushlet, expects a literal to be in the next address. So that one is actually a literal. This is not a call instruction. It's actually a pushlet one. But, you know, if you see a plet, then you need to be smart enough to ignore the call that's right above it. And I can do that. And I'm the only one using this so far. Probably only one ever. So I did a lot of work with this before I ever tried anything else. And before the virtual machine really seemed to work. And Greg Bailey had always said, wouldn't it be cool to use a working virtual machine to test a new not working yet virtual machine? Are you saying hurry up? Oh, okay. We fit Polyforth here in this section, as it usually is, except that I took away one node from Polyforth and gave it to the C virtual machine. C virtual machine is up here. They both have access to memory. And the breakpoint, when it runs in the C virtual, this one uses page 0 of SRAM memory. This one uses page 1 of SRAM memory. So they can run without hurting each other and use all the memory they can get access to in 16 bits. When the C machine executes a breakpoint, one of the things that it does at the end of the breakpoint is disable its own access to SRAM so that it just sits there waiting to get the next instruction. And Polyforth can go and read. Basically, it can look through all of page 1 memory, can decompile, disassemble what's out there. So Polyforth, we know works. We can use it to single step through and debug a C program in a different page. And this is what my Polyforth display looks like. I've got the registers I care about up here. And I have a memory display here, addresses, and I put the current instruction close to the middle so I could see a little bit of what's already happened and what's going to happen. And it disassembles very similarly to array forth. See that call? It's not really a call. It's really a. Oh yeah, it is really a call. I'm looking the wrong direction. That actually is. That's the break. That's calling the break instruction. Okay. And LLit is the next instruction that will be executed when I say go. And then there's a way in Polyforth. There's a word that will restore access to SRAM for the C machine, and it'll go execute until it hits a break again. And that's been really fun, and it works. So the C compiler, Stefan told me last week that he's finally finished the last two parts that he was worried about, which was struct and unions. And he says he knows there's still some bugs, but he's going to get me a copy of it next week. We'll start testing it some more. And I would like for us to encourage Stefan to give us a talk about the actual working C compiler at a later date. And I'm looking forward to that. And I'd like to thank Stefan for that wonderful work. Oh, and I just spelled magnificent. Oh man, I hate that. I guess that's it. Any? Yes. Should I come out there?
Will the specifications for the virtual machine be publicly available, or is this an internal project?
Right now it's internal, but I don't see what good it would do for us to not publish it because we want to use it for marketing. So I'm assuming that when it's working, it's going to be out there. Yes. Yeah, absolutely. Anybody else? Yes, Peter.
So how does the performance of the virtual machine compared with either the Polyforth virtual machine or native code, or what do you think native C code?
Right. Well, native C on this machine, that's not, I have no idea about that. I only have anecdotal evidence because I haven't done any actual tests, but it's pretty obvious to me that when you're using a stack frame, there's a lot of, it's like load and store architecture, you know, you have to go get the thing from wherever it was and put it here, and then get the other thing from there and put it here, and then execute your function. And you can't just do them on the stack like in Forth. So absolutely, it's going to be at least, I mean, absolute best you could hope for would be half or a third as fast, I would think, for things like that. So, I mean, when I was talking to Stefan, I was saying, let's really trick Greg and let's make something even better, you know, something so good that people would actually want to use it. But the more I look at it, I don't think that's possible. I think there's always going to be a disadvantage to it. But something I learned from Stefan, and maybe everybody here but me knew this, but when you use a C compiler, you compile a bunch of code, you go compile library code, whatever. It's all compiled in some temporary intermediate format, and then the linker or the linker loader goes through and figures out which ones you're actually using. And apparently, and I never knew this, it doesn't even put any dead code in your machine. Yeah, well, Stefan says ours is going to do that. Okay, so maybe okay. Stefan explained to me that the linker, and sometimes I guess the loader, I don't know, decides what actually belongs in there. Starts at main, goes through and looks and sees what things get called, make a space for that, you know, fix up the addresses. So that's something that, you know, in Forth, you got to use your own brain for that. I mean, that's the one thing I've seen that I thought was kind of cool about C versus Forth. Anybody else have a question? Ian.
Any issues with like foreign function interface, so calling Polyforth from the C machine or vice versa?
Well, there's no issues because we haven't tried it yet, but calling functions from one to the other, absolutely, it's doable. I just don't know if I want to. See, I have a hard time deciding, am I just using Polyforth to test the C machine, or do I want Polyforth to always be there? And I don't honestly know the answer to that. right now, there's no interactivity except through Polyforth. There's going to be access to the rest of the, to the I/O through C. I'm sorry, I don't have a good answer for that. Don't know. Yes, Sam, right there.
To touch on that last question a bit, even on contemporary desktop machines or even laptops like this, foreign function interfaces are incredibly big, baroque, ugly, suboptimally performant. It's actually gotten to the point where, quite literally, you're almost as good just writing a blob of data into memory and just sending a message to another process saying, "Here's this blob of memory. Do something with it."
But how do you really feel about it, Sam? I'm just kidding. Yeah, it sounds awful. Yeah, it sounds difficult. So it's probably not on the top of our priority list, but we'll see. Anybody else? Okay. Thank you. 10-minute break and then fireside chat with Chuck Moore.
Try them. The problem is that I don't know how to solve is the loop. Okay. It'd be easier because I want to experiment. I want to try doing that someday, but I'd want to try it first. I figure I'll need it next year. Okay. I will work on it this year on how we can do that without introducing a loop. See, with this my computer, it knows that there could be a feedback. It doesn't allow me to hear that mic. I don't hear that mic. And so it eliminates the loop. If I introduce another mic, we've got a loop back. So I've almost got to do it with this mic. And I haven't figured out how to do it. It's how do I make it so that they don't echo? So it doesn't echo out to the internet.
So in sort of the same direction.
It's a problem. So let's do as best you can. We'll see how it goes.
It worked last year.
I will work on it. We've been wanting to work on something like that. That looks like it's on.
This room is a little bit echoey.
There's the problem. We tried to do it without that mic, and it's really bad reception. We've got to figure it out.
If we don't have enough electronic talent here to do it,
we do. Just experiment. Using inline literals, basically saying.
two sticks. One pushing the I'm not that old. When he's going back, he's popping food.
Sort of problem.
That's a good fire.
Just the whole data center went away. One day it's like, why is my job not running? Oh,
That's right.
yeah. Better about myself. How did you get sucked into?
You know, it does like touch upon.
walking back and forth.
-4 minutes.
Come on.
Your PC's saying that it's going to restart. Oh, yeah. Stop that. Close.
Shoot. It'll probably do that again, huh? $13.68.
Before Chuck starts, I wanted to say I've got a 37-inch LG TV, about 8 years old, that just died one day. There's enough information on the web and enough spare parts like motherboards and power supplies that I think that it would probably not be too hard to resurrect. I want to just put it into the silent stream. If there's anybody that wants it gratis that is in this area, I will deliver it to your house. Thank you.
Good day. This is the 2015 fourth day fireside chat by yours truly, Chuck Moore, chipchuck@colorforce.com. I am here to entertain you. In previous years, I have been here to educate you, but I haven't got anything to teach at the moment, so I will start by telling you a little bit about me, because that tends to be uppermost in my mind. I live in Nevada, 250 miles from here, in the desert, with a view of the Sierra Mountains. From where I live, I've got, 270-degree view, perhaps, 180 degrees of the Sierra. I can see 3 passes. There's Ebbets Pass, Sonora Pass, and Ebbets Pass, Sonora. What's in between them? Oh, there's a 3rd pass. And there's 2 more to the south and 2 more to the north. So I've got lots of passes, although I can't see them all. And I do a lot of hiking. I've got another, this is my master plan. Life force, decompile, and then discussion. First, let me apologize for my voice. I don't talk a lot. I live alone. This is my one talk this year, and my voice has just gone rusty. I don't know if there's anything I can do about it. I've been drinking Coke. That might help. Well, this is a brief view of my life. Jump down to health. That's relevant to my voice, I suppose. I'm in good health. I do a lot of hiking, 10 miles a week or so. That's 500 miles a year. That works. I've recently started lifting weights, 5-pound weights. I'm trying to transform fat into muscle, and I'm told that's the only way to do it. The exciting thing this year is the Medicare enrollment period. My wife set up some Medicare supplement policies 10 years ago, 15 years ago. And I have refused to be involved with Medicare. It was just too complicated to wrap my mind around. Until this year when I decided, come on, it can't be that bad. It almost is. What I have done is traded my supplement plans for an Advantage plan. Everyone knows who's involved in Medicare, I suppose, the difference between them. But I've got a good Advantage plan. There's no premium, there's low co-pays, probably due to my position in the desert where there aren't very many people, and that maybe helps. The trade-off, as I see, with the supplement, I didn't have many co-pays, any co-pays. It was costing me $3,000 a year. With no premium, I'm gambling that my co-pays are going to be less than $3,000 a year. And that is almost certain unless I get in the hospital, whereupon it's probably the same. So there's this opportunity to trade certainty for a gamble which is under my control and might work and might not. I wouldn't mind saving $3,000 a year. It's particularly good for prescriptions. I was paying $50 a month for a prescription insurance. And I was paying maybe $10 a month for prescriptions without an insurance plan. The gimmick here is, as the government likes to do, if I didn't have a prescription, I'd be screwed for the rest of my life because they would be charging me premiums in the future.
Higher premiums plus penalty interest.
Now, they apparently have not done that with Obamacare because nobody is signing up for it. The penalties are not sufficiently great that people are willing to buy premiums when they're healthy. So we'll see how that goes. But anyway, health is interesting. I'm going to try to stay healthy. I'm going to try to keep hiking. My house is the smallest house I could find. It's 600 square feet above a two-car garage. It's at the end of a 1.5 mile dirt road, 5 miles along a secondary road from 395, a primary road. So it's pretty far out. And every now and then I get someone like the DirecTV installer who finds his way out to the end of the road or doesn't. FedEx sometimes gets lost. UPS pretty much knows where I am. I'm Amazon Prime, so I get things delivered for free. And that's got to be an advantage for me and my position because it costs me $25 to drive to the supermarket. So it's best if they deliver it free. It's an ideal opportunity for a drone to fly down my road and drop something in my yard. That would be fun.
Just publish your coordinates.
I got my coordinates. I got them half a dozen different places. I can never quite remember what they are. But I can Google Earth me and see me sitting out there. Oh, 53 seconds. It won't go away as far as I know. I don't know how to make it any more emphatic than that. Okay, let's go to Wi-Fi. I've got a Media Link, very nice router. And it's got all this connected to it. I've got a PC, I've got a Mac, I have an iPhone, actually have an iPad also. I've got a smart TV, which is internet connected. I've got a weather station, which is internet connected. And I've got Echo. Do you know what Echo is? Echo is an Amazon device. It's a little cylinder bigger than a Coke can. And I talk to it. It is the nicest voice device that I have encountered. I've got, what's her name on my iPhone? I've got something on my Siri. Yeah. This is Alexa. Alexa's very smart. What happened was I have a lamp called Blue Max. It's a reading lamp. And Blue Max, I thought twice or three times before buying it because the biggest complaint was that the switch fails. But I said, okay, I don't care about that. It's a bright light. It's fluorescent. It's bright. It's got more lumens than anything you'll ever find. And it's just a joy to have there so I can read. But after a year or year and a half, the switch broke. Fortunately, I fiddled and fiddled and fiddled until I got it broken on. So all I had to do was unplug it and plug it back in. And then I read about this Belknap, is it? You put a thing in the wall and plug into that. And I can control it with my iPhone. My iPhone will turn it on and off. Well, this wasn't really so convenient. It's easier to plug it in and unplug it. But then I read about Echo, and Echo can control this, this interface. So I bought one. And it works beautifully. I say, Alexa, turn on Blue Max. And the light comes on. Alexa, turn off Blue Max. It cost me, I think it's $200 or so for Echo, and it was $50 for the plug-in one. So for $250, I have a switch. But it's fun. And I'm gradually learning what else Alexa can do for me. If I ask her, Alexa, what is 16,000 divided by 65? She will come back and tell me whatever it is. Apparently she has access to MATLAB, or something like that. No, Wolfram. And Wikipedia. And can answer lots of questions. And it's sort of an unknowable repertoire. Because if I ask her, what is the Dow Jones Industrial? She says, I cannot tell you that. Not, I don't know, but I cannot tell you. So there's some kind of licensing involved, probably. But anyway, a joy to behold. She's always on. I just say Alexa, and it's a plug in the wall. Whereas with the iPhone, I've got to push a button, I pull it out of my pocket, whatever. So I highly recommend Alexa for your edification. It's also quite a, I'll get to this later. My weather station's nice. It required another device Ethernet connected to my router, but I've got a weather rotor and yes, one of those, and a temperature and precipitation. Now, precipitation is guaranteed to be 0, but the temperature is interesting. And the barometer goes up and down, but I don't pay much attention to it. What this device does, the data is read from the station by the little Ethernet box and sent to a website. And I can retrieve that data by going to the website and looking at my own data, which is coming from 200 feet away. But it works. I can look at it here from my iPhone, and I don't have to have another display device hanging on the wall or sitting on the table or wherever. So that's exactly what I wanted for that. I do a lot of reading. Currently, I am reading Stone Barrington, Stuart Wood's character. He's got 30-odd novels. He writes 2 or 3 a year, not like your lazy author who only writes 1 a year. And they're good stories. I enjoy them. They're kind of, well, mystery thrillers, but they're fun. And I found that my library, which is 25 miles away, has most of them. Ones they don't have, I can get on Kindle. I can get lots of books on Kindle. They have a lot of nonfiction, which is hard to find anywhere else, bookstores or libraries. The problem there is graphics. Kindle graphics are terrible. Even Kindle equations are terrible in the sense that I magnify things on my big screen and I can read it without my reading glasses until it comes to the equation. The equations tend to be low contrast, small, and just impenetrable. So there's room for improvement, but nothing I can do about it. Let's jump down to driving. I used to spend a lot of time driving in the desert. I was maybe looking for a place to live, or maybe just enjoying the wide views, or breathing the sage. But I really enjoyed that until I moved to the desert. Now there's nowhere I can drive to that is any better than where I am. So I tend not to drive so much. My Jeep is 2 years old and has 25,000 miles on it. On the other hand, my driving is under the mountains. I have no trees. I can see some small pines on the hillsides, but the trees are all in the Sierra. I can drive to a trailhead in an hour and have all the trees that I ever would need. And so that's what I do. I just commute back and forth to trailheads. For my 3, 4, 5 passes, the PCT crosses them, and I've got 10, 15 hikes. Oops, did I miss it? Come on. I don't know what that little circle means. It means, well, but it appears in times that I always surprised at it. Why would it have gone? Okay, well, you saw that one. I'll worry about the next one when it comes. Like a blue screen. So I don't drive so much, or I don't drive in the same way as I used to, but that's all right. The other thing down there was movies. Yes, I have DirecTV, TCM. I had Stars. I used to watch a lot of movies. I conclude now that I've seen them all. And I browsed around for a movie which I'd like to watch, and there aren't any. So I've canceled Stars, which saves me $15 a month. TCM is still there, but I rarely find a movie that is interesting. Oh. Pondering. I do a lot of pondering. That's my other hobby. I ponder the huge and the tiny. We are roughly in the middle of range. There's about as much universe stretching out there as there are microverse underneath. And they both contain large problems, which are fun to think about. Especially when I'm trying to go to sleep at night, I always visit those realms. The human body is arguably the most complex mechanism in the universe. No one has ever studied it before. No, there isn't any book we could go to and read that someone else wrote. We have to discover everything we'll ever know. And it isn't even clear that it's knowable. It wasn't designed to some kind of plan which we can decipher. It happened. And we hope that it happened in a way we can fathom, that will make sense to us, but we don't know that. I've been studying molecular biology, I've been reading some books on molecular biology. And there are a lot of very interesting characteristics of the way our cells work, the way our cells communicate. And I can't imagine that that doesn't have some relevance to computers, artificial intelligence, human interface. Lots and lots of realm. That's the nano realm. The nuclear realm is orders of magnitude smaller and more mysterious even than that. In fact, you get down to the micro realm where you're dealing with bacteria. And there's a whole fascinating subject there. I finally found the number I was looking for, and that is about 10% of our mass, body mass, is bacteria. We have 10 times more bacterial cells than human cells, but they're small. So it comes out to only 10%. The most important bacteria are in your gut. And this goes back to health. Your gut biome is crucial to your health. And this is not generally appreciated. But there's arguments that Alzheimer's is due to a gut imbalance. That your gut communicates with your brain. In a sense, you can control things by what you eat. I'm just learning about this. It's fun. So that's the medium realm. Then, of course, the realm of the solar system and the galaxy and the universe. I remember a long time ago, I was talking about fourth, and the justification for fourth was that software establishment was incompetent. This was 40 odd years ago. The software establishment has not budged. it is, at the time, I thought the hardware establishment was doing a good job because they were coming out with these transistors and these computers and doing wonderful things with architectures. But no, the hardware establishment is, one, conservative, and two, incompetent. Now, these are the fields I know well, and I think my opinion is well-founded. But the medical establishment is conservative and incompetent. The political establishment, forget about it. They aren't even capable of a measure. The world can't deal with a handful of terrorists. This is distressful. I mean, these people should have been stomped on several years ago. And they're still debating and arguing and but to get back to the medical establishment, they don't know what they're talking about. Or what they're talking about was 10 years old. The federal food pyramid is intended that the federal government can tell you what to eat. And they're telling you wrong. Let me give you, without medical advice, my opinion of the most healthy food you can eat. And that is saturated fat. That is, and has been on their list of no-nos. Whole grain cereals, breads, terrible, inflammatory. They will do you in. They don't do your bacteria any good either.
But you want to emphasize that this isn't just your opinion. There's good science to back all this up.
Google this and you'll find the references, but they're new. They're sitting in the last 5 years. These ideas have been not only put forward, but documented. And the establishment is not catching up to it. You keep reading advice like eat whole, heart, healthy foods and avoid fats or healthy vegetable fats. Vegetable fats are not good. The worst thing you can eat, in my opinion, is Coke. It's my favorite food, has been for decades. I hoped it would soothe my throat. It hasn't done a whole lot of good. But it's got fructose. Fructose is very bad. It screws up your sugar metabolism, as bad as alcohol does.
And phosphoric acid for your teeth.
Yes, teeth dissolve in Coke. So I've been trying to eat well. I didn't have lunch because there was nothing that really appealed to me. A green salad might have worked. But so many foods are, I worry about them more than I enjoy them. I had a beautiful dinner last night at the Sea, which is near Dinah's restaurant, or Dinah's Hotel. It's a seafood restaurant, expensive, but I had a lovely salmon, grilled salmon with dressings. I don't eat much. I can't eat much or I'll gain weight. I'm trying to keep my weight stable. And that's one of the reasons I do the hiking. I can burn a lot of calories. And it does seem that calories are the important measure of your diet. But most of the calories should come from fat, saturated, good animal fat, which means practically speaking, steak. It's okay. Are we back yet? What was I going to talk about next? Okay, I'm just about finished with life. I want to talk about fourth. I have a whole lot to say about fourth, but I have always viewed for the last, 40 years, that fourth was a low-level language. High level, low level, both. But I concentrated on the low level. I kept writing fourths for every machine I could see and optimizing them as best I could, although Greg seems to have done a better job of optimizing than I have. I am now thinking of fourth as a high-level language. I'm tired of writing compilers. I want to see what I can do with topics like artificial intelligence. Get back to Alexa. Alexa is a form of artificial intelligence, the most impressive that I've seen, that's in the cloud. Now, none of the intelligences I had seen were in the cloud. They were all in mainframes that filled a giant room, or pocket artificial intelligences. And here's a case of taking advantage of a technology that didn't exist until recently to really multiply the power of computers. I don't know how she works. I don't know how they work. I'm sure that my request, my digitized voice, is relayed to a server somewhere in a server farm, which sorts everything out and generates a reply and sends it back to me. It takes a ponderable amount of time to do that. It doesn't cost me anything. And there's no limit to how that can develop. I'm impressed by how well she recognizes my voice. My voice is always a problem. But I say, Alexa, turn on Bluemax. And I say it at different speeds, different blurrings, different facing in the wrong direction. And she gets it every time. So that's what we can do with artificial intelligence today. But is it really that difficult? Is voice recognition really that difficult? Or haven't we hit upon the simple algorithm that the brain uses to do the same thing? These are all topics to explore, but at a high level. It doesn't matter how fast Forth is running for me to be able to ask these questions of it, to organize an architecture which works. I guess it's just bad luck that they choose to. Light's blinking. That's an interesting thing too. The light blinks when it goes through the hard drive. It's always going to the hard drive. It can't do anything without going to the hard drive. It's only got a gigabyte of RAM, I guess. Fourth, intelligence, Alexa, high level, low level. Okay, let me go on to decompiler. I mentioned this last year. I didn't provide any details. I'm going to provide more details now, but I can't tell you how to write a decompiler. I've written a couple. The motivation for this was the G8144. It's a marvelous motivator because it changes the paradigm, as you've seen today. You've got to organize the task into these little nodes, distribute the computation across nodes. And I find that delightful. It's a fun thing to do. And you've got up to 144 nodes running in parallel. You can do a lot at the same time. It's true parallel processing. With true effective communication among the nodes without much shared memory. You don't need shared memory particularly. Oh, hey, what? It's not talking. It's, I don't know if it, maybe it can't do that. I'm hitting the buttons. Decompiler. So what I did was I wrote a compiler that ran on the 144 and generated code for the nodes. And that became awkwardly difficult. I didn't like that much. I was compiling from source code in SRAM every time I wanted to load a node with something. It occurred to me that it would be better to load machine code from SRAM and then have a decompiler which would show me what that code looked like for each of the nodes it was running. And I coded it, and it was nice and simple and small compared to the compiler. There's two phases to writing a decompiler. First, you take your object code and you display it as forth, as color forth, of course. And then you write an editor that lets you change that object code, which is a simpler process than actually a compiler, but it's similar to a compiler. You edit your object code directly, and then you decompile it to see what you've done. That's how far I got. I hadn't gotten the editor to work, although I've no question in my mind I can. But I moved on to other things. About this time, I got my iPhone, and I wanted to write an app for my iPhone. So I became a, what do we call them, a developer, an Apple developer. And I learned to write Swift code. Swift was brand new at the time, so there wasn't as much documentation as there is now. What did I do? I wrote a forth in Swift, but of necessity it was interpreted. It wasn't compiled. And this I knew was going to be slow, but it was the first step. About that point, I moved on. I got a Mac Mini, and I wrote a home page for the web, and I did it in JavaScript and its associates. And then it occurred to me I wanted to do that in Forth. So what I figured I would do is decompile the JavaScript into Forth. Now, in order to do a decent job of that, you have to restrict the structures you use in JavaScript. You know, only use the things that you can decompile into Forth. But that's quite practical. And I left that at that point. I didn't actually get the decompiler from JavaScript or from Swift. Now, on the PC, they have a language called C#, which is, I suppose, pretty close to C, as Swift is pretty close to C. And I could write a decompiler of Forth in that also, but I haven't got around to it. Don't know if I ever will. I got the iPad to serve as a touchpad. for the other computers I had. And I played around with that. It's not been satisfactory. So I could write an app that would do that the way I want it done. That will do. Ah. But what I have done E-D-I-T. I don't think that matters. I just can't type. Decompiling. What I did do was lay out a circuit board for green arrays, although they don't need such a circuit board. They can do their own. With a 144 in it and enough peripheral circuitry, reset, decoupling caps, what have you, to make it functional. And I did this in Gerber, which is the standard file format. It's an ASCII format. Ugly, ugly format. You've got to have 5 decimals after the coordinates. So your coordinates are all full of zeros, trailing zeros. And the looping constructs are clumsy. It's just a clumsy, clumsy language, in spite of the fact that they just upgraded it a couple of years ago. The new version, the old version is deprecated, and it's worse than before. But I guess they know what they're doing. So I said, okay, I will take the Gerber, I'll decompile it into Forth, and show how it ought to be done. I did that, and I was very disappointed in the result. There's a certain level of complexity required in describing PC boards that Gerber has pretty much pinned down, and I can't do very much better in Forth, or at least I haven't figured out how yet. So that's pending. The GDS is the file format used for chips as opposed to circuit boards. And it's binary, but that doesn't matter. I thought when I designed 144, I was generating a GDS file. I generated it from Forth. I wrote a Forth program that described the chip, and then I translated it into GDS. Were I to do that again, I would start with the GDS and then decompile it into Forth. The two are more or less one-to-one compatible, or at least the subset of GDS that I was interested in. And the net upshot of that is that you can take any programming language and decompile it and make it look like Forth, if there's any reason to do that. My reason for doing it is, one, I think in Forth, and two, I find the Forth syntax a lot more readable than all the varying syntaxes of these other languages. And there are many of these other languages, whereas I can learn one, I can learn Forth, and I can deal with all the other languages. Now, the world has changed. My first fourth was native. All of my fourths have been native. Greg gave me his version of array fourth that ran under Windows. I don't know how to compile assembler fourth any longer, or machine fourth any longer. It looks to me like the only practical thing I can do in the remainder of my career is cope with these other languages and let the operating system and the graphics interface and all do the things I love to do, touching the hardware. But get on with high-level fourth and try to solve some pending problems. My language of choice is JavaScript, ironically, because it is available for any of my devices. Again, this is only one language that runs almost everywhere. It's not fast because it's interpretive, but it's probably fast enough. Now, what I did was I wrote a fourth in JavaScript. I wrote a fourth interpreter in JavaScript. And I got it working. And the unhappiness I had was that I had an interpreter interpreting an interpreter. And this is 2 levels of ugliness. And so I decided what I would do is write a decompiler for JavaScript that made it look like fourth and yet was as close to as close to the hardware as JavaScript would allow. Except today I heard that maybe you can get even closer with a couple other versions. So we'll see about that. But this is an approach that I have to recommend. It's easy to do. That's why it's I would recommend it. It's easier than writing a fourth compiler. If you actually want to start a new application in this way, you start with a blank sheet of paper, you put some boilerplate on it, and then you start editing it with your fourth decompiler editor. Now, the easiest way to get started is to actually write the JavaScript that you are going to be decompiling. Get your decompiler to do it. The advantage here is that the JavaScript is a contemporary language, full of punctuation, full of parentheses. And a characteristic of it is that it has 3 or 4 different kinds of parentheses, the curly brackets, the square brackets, the curl brackets. And you got to get them right because it's not going to anticipate what you probably meant. So all of the errors you make in writing JavaScript or C are easily caught by the compiler, easily corrected by a compiler that was remotely smart, and totally irrelevant. Then when you get a little application, like I would do an iPhone app, my current iPhone app, which I haven't actually downloaded even, is a tally counter. You push a button and it counts. It maintains a counter. This is not hard to do. The hardest thing was to position things and to get the background color right and so forth. My tally counter is better than any other tally counter out there because it has only 1 button or 2 buttons, reset and count up. The others insist on being able to count down, which is, to my mind, silly. Why would I ever want to decrement my tally counter? But anyway, that's my motivation. Also, I've got 20 or 30 apps on my iPhone. And each one I use a tiny fraction of in a particular circumstance. It's a nuisance. I would like an app that does all of the things that I want to do, only the things I want to do, and I can replace all those other apps. One of my goals is to read the accelerometer. I haven't even gotten close to that. I can page through some things. For instance, what I would like to know, I walk. I have a walking app. It keeps track of distance and time and elevation. But elevation is 2 pages away from distance. And I would like to see the distance and the elapsed time and the actual time and the elevation profile and the map all on one screen at the same time. Why not? But no one's ever going to do that for me because they want sharing. I don't want sharing. Why would I want to? Who in the world would be interested in where I'm walking or how far or when? So I don't need that. And that seems to be one of the major thrusts of all these applications, is to be able to share your experience with your vast repertoire of friends. So my apps would be different enough that I'm almost motivated to do them. On the Mac Mini, the one that's driving my big screen, again, I would like easier ways to access the various websites that I'm going to. Some things I can do that way, some things I can't. I have to go back to the menu bar. Didn't get email. I can't get email from my screen. With a properly organized JavaScript, I probably could. Hello, decompile. Doesn't matter. I just about run out of displays. I wanted to show you those screens because to remind you that they're all done in Colorforth. That is just what Colorforth source looks like. I spent a day or two with a cloud version of PowerPoint so I could have more professionally looking screens to show you. And I eventually gave up. It was just too much work, drawing little boxes. And what I wanted to do is show you some pictures. Now, I never did figure out how to get a picture and text on the screen at the same time. So those of you who can do PowerPoints, I admire your skill, but I don't relish acquiring it. Life is full of interesting experiences. One is a book I read recently, particularly the title of it, but it was distinguishing between materialism and experientialism. Experientialism is really an ugly word. I have to pronounce it in my mind before I can speak it. The book is called Stuffication. It has to deal with all of the stuff people are accumulating and how you'll be happier if you get rid of most of it and enjoy life. And one of the points they make is don't take pictures. Enjoy the moment rather than taking a picture you're going to show to somebody else in the indefinite future. Another experience was this little thing. I had to drag it out of the closet in order to have anything to be able to show you today. And its battery has died. That's why it's plugged in. And I said, by damn, I could buy a new battery for it. So I went to Amazon and I started looking for batteries, and there they were. You get the replacement battery for this for $250. You can get a third-party battery for $70. And I would have done that, except I started reading about third-party batteries and how they can explode or light on fire or something. And I thought, I don't really want even one of those in my closet. I just don't know the level of threat. And all of that to save having to carry this power supply to this meeting, I didn't do it. The web is full of knowledge. Almost any question you might ask, you can get some information about, whether it's accurate or not. You just have to sort of weigh the evidence and decide for yourself whether that is of value to you. I do that with my medication. I've got 3 prescriptions. One for blood pressure, one for cholesterol, and one for thyroid. And I just last week learned that my thyroid medication will lower my blood pressure in addition to whatever it's supposed to do. Do I believe that? Well, it's nice. If they said it would raise my blood pressure, then I would have to explore it further. But this is a good effect, which might be true. I'll be finding out. Same with food. You can get any any diet recommendation you want. The one thing that they don't all agree about everything. Some like vegetables, providing those vegetables grew above the ground. Below ground vegetables are different somehow, starchy. Establishment believes in fruit. Websites I respect say that fruit is nature's candy. And the reason we like it is because it's high in sucrose. Sucrose contains fructose. This is not, well, fish. The thing about fish is it's got omega-3. Omega-3 is almost universally deemed a good thing, except for one reference I came up with recently saying people are overdosing on omega-3, and what you need is a balance between omega-3 and omega-6. The Paleolithic diet, our ancestors did not eat fish. So they were deficient in omega-3 and got along just fine. So where's the truth lie? We've got to have, in addition to a competent medical establishment, a competent research establishment that explores these things and comes up with the right answers. These are yes-no answers. And the problem, almost certainly, is that the effects are subtle. You need a large-scale clinical double-blind trial in order to detect whether this is good for you or this is bad for you or how much. And that's going to take the next 100 years maybe. But maybe in 100 years, they'll have sorted it out and they'll know what is good for us, what is good for our gut bacteria, and what we should do in our diet to optimize this. But it's not going to happen quick. And it's always going to be the maverick who says, everything you thought was wrong and what you really want to do is this. It's interesting that we've got this problem in spades going to Mars. What are they going to eat? Freeze-dried food for 2.5 years? They can grow their own vegetables. You saw them grow their vegetables. This is NASA at its finest. They grew a tray this big, and each astronaut got a leaf of lettuce. And then they took the rest of the lettuce back to Earth, and they ran tests on it to see if it was really edible. NASA is wonderful. They're the only people in the world that are doing anything interesting. And they're doing it right, with a large program, great redundancy, dedicated people. I don't know how many. Hundreds of thousands, surely, of people, if not millions, working on this Mars project. It's a good thing. I'll support it. But boy, they can turn it into a bureaucracy. There ought to be a anti-bureaucratic movement. And the Republican candidates hint at that. Some of the tax plans are going to get rid of the IRS. They don't say what they're going to do with the IRS employees. Are they going to fire them? Are they going to dump them back on the job market where there's no market for accounting clerks? Well, it's fun to watch the campaign, but it's not going to turn out well. And that's about all I have to entertain you with. The last thing on my list was discussion. So if, having told you what I want, having said what I want to tell you, anything you want me to say, I would be happy to address. Decompiling. That's right. I don't know. It could well, but in my particular take, it wouldn't. It would not be full-blown C. It'd be a version of C which was easily decompilable, meaning I would avoid some of the more hideous constructs. Hey, good. Yeah. But then what would you do with the fourth? All I'm doing with the fourth is displaying it. You could print it out or put it in a file. Well, yeah, but okay, yeah. I would say that you want to go back to first principles and write an operating system. That the way they've done it is suboptimal. And it's suboptimal in whatever language it's written. But by all means, give it a try. If I don't have C on my list, but I do have C#, and I might be doing that. Depends on what I want to do is write a text editor that with a little bit of configuring can deal with any of these languages. And C would certainly be one of them.
Sir.
Sure.
When you were doing the GA 144, did you ever explore any other method of making an array besides a American prairie town rectilinear grid? For example. Well, you know, they've got the city of Paris. They've got, you know, there's semiconductors on a sphere. There might be a geodesic network. I don't know. I just wonder. I mean, there are lots of different kinds of arrays, and there are less arrays that work than arrays in math. So I just wondered if there was any work in that era of trying to find a better array than flat out on the table.
The thought crossed my mind. I thought of hexagons, a hexagonal array of nodes. But there didn't seem to be any advantage, and the rectangles were easier. All of the nodes are the same size and shape. They do form a dense array. One of the things we've considered is putting more memory on chip. If we were to put a kilobyte of memory, it would take the place of maybe 6 of these nodes. And so you would have a mixed array of big things and little things, which is possible, but so far has been unattractive.
Could a node like die or change into something else? Like if it needed to be a a memory location? Could it like physically change from being a regular orthographic thing to a specialized? It seems like you already are specializing because some of these nodes at the edges have certain wires attached.
That's right.
But that doesn't. That's not true in the center, right?
No I/O in the center. Although people argue we could do that, and it's some long wires. You can. Each node has 64 words of memory. And if you need more than 64 words, you can talk to your neighbor and use his memory. You say, store this there and read this back. And he can talk to his neighbor. So you can construct up to 9,600 words of memory by chaining nodes together. And we do that, and it's a perfectly excellent thing to do. To actually have a lot of memory on chip, I have always fought against. You can buy memory chips. But what we've got is a CPU cycle chip. You've got the maximum number of CPU cycles. How many of those would you sacrifice in order to get how much memory? The trade-off there. And so far, I think 64 words works well. I keep getting emails recommending these from time to time. No serious attempt on the part of Green Arrays to do it, with the exception of there was a Bucky tube memory, which is supposed to be fast and low power. But the odds of being able to do that with the fabricators we have are negligible. It's all cutting edge. A lot of it's vaporware, and I'm sure Greg's attitude is we're going to be conservative. We're going to do what is tried and true, because if we can't sell the chips we've got or their derivatives, we aren't going to be able to sell anything fancy.
Where do you get your water out in the desert? Where do you get your water? Do you have a good well?
I've got an excellent well. I'm on a alluvial fan, and the water flows from the mountains by 2 miles away. And my neighbors assure me that they aren't taking my water, that there's plenty of water for everybody.
Yeah, that's...
My well is 180 feet deep, 90 feet underwater. So that's reassuring. On the other hand, if I have no electricity, I have no water. And the first thing that's going to go when the catastrophe strikes is going to be electricity. I'm way out at the end of the electric line. So they're going to be, I'm the last one that's ever going to reconnect. 2 minutes? Yes, I have done that. That's always been the way I laid out my circuit boards until now. And now I am abandoning that approach for 2 reasons. First, half your chips are metric, half your chips are English, and there's no way to put them on the same grid. Very relevant. The only thing I have that he doesn't is I'm decompiling instead of compiling. And I think that is an approach which needs to be tried. Maybe in a year I can show you the code and show you how nice and simple it is and how elegant the descriptions are. But I said that last year too.
functions, but if you write simple JavaScript, it will compile it.
That sounds the way to go. Yep. Okay. I guess that's the 2 minutes. So thank you for listening.
Please make your way downstairs.
Pressure tank.
Some people have to leave, so we need to get that done quickly. Don't stop and pack up. You can do that after the picture.